GCE Advanced Level Chemistry Practical Series Experiment number 25. Examination of properties of alcohols. The aim of this experiment is to observe the reactions of OH groups in alcohols. So the aim of this experiment is to observe the reactions of OH groups in alcohols. So let's take a look at the introduction. Alcohols are compounds containing an OH group attached to sp3 hybridized carbon atom. Alcohols with one OH group are called monohydric alcohols, while those with 2, 3 or 4 etc. are called dihydric alcohols, trihydric alcohols, tetrahydric alcohols, and etc. Compounds with many OH groups. Compounds with many OH groups are commonly called polyhydric alcohols. So students, based on the number of OH groups present in the alcohol, we will be giving them, or we will be characterizing them under different classes of alcohols: monohydric, dihydric, trihydric, and polyhydric. So students, when it comes to our experiment that we are conducting here, we are mainly working with monohydric alcohols. We are mainly going to be working with monohydric alcohols. Classification of monohydric alcohols. So like I mentioned earlier, we will be mainly working with monohydric alcohols, and now we are going to look at the classification of monohydric alcohols. So similar to the alkyl halides, monohydric alcohols are classified into 3 types depending on the number of hydrogen atoms attached to each carbon atom bearing the OH group. So based on how many hydrogen atoms are attached to the carbon atom that is bearing the OH group, we have characterized monohydric alcohols into 3 main classes. Carbinol carbon atom as primary has 2 hydrogen atoms, secondary has 1 hydrogen atom, and tertiary has no hydrogen atoms attached to it as shown below. So what we have over here is primary, secondary, and tertiary. So before I explain to you what primary, secondary, and tertiary, take a moment to observe and see if you can identify what primary, secondary, and tertiary alcohols are. According to this paragraph that we just read, based on the number of hydrogen atoms attached to the carbon atom that is bearing the OH group, we can characterize alcohols into different classes, right? So we say primary, secondary, and tertiary alcohols. So on the carbon atom that has the OH group, if there are 2 hydrogens, we call that particular type of alcohols primary alcohols. If the carbon atom bearing the OH group has only 1 hydrogen, that is classified as a secondary alcohol. If the carbon atom bearing the OH group has no alcohols, that means it is surrounded by only alkyl groups. At that point, students, that is referred to as a tertiary alcohols. So over here, we can see we have primary alcohols first. Now this particular alcohol is a primary alcohol, and this one is a secondary alcohol. We can see carbon bearing the OH has a hydrogen here. Over here, carbon bearing the OH has 2 hydrogens. So this particular carbon has 2 hydrogens. Here this carbon has only 1 hydrogen. And in this particular structure, we can see the carbon bearing the OH has no hydrogens. So this is going to be our tertiary alcohol. Another way of looking at it is, if you take a look at the carbon bearing the alcohol, if you have only 1 alkyl group attached to it, you can see over here, this particular carbon bearing the OH group has only 1 alkyl group attached to it. At that point, it is going to be referred to as a primary alcohol. And when you have two alkyl groups attached to the carbon bearing the OH group, that will be known as a secondary alcohol. And when carbon bearing the OH has three alkyl groups attached to it, that is known as a tertiary alcohol. So you should be able to, by looking at these different structures, determine whether the alcohol you are working with is a primary, secondary or tertiary alcohol. Let's move on. So when we are conducting this experiment, we will be needing some equipment as well as some chemicals. So let's take a look at the equipment and the chemicals we'll be using for this experiment. We have litmus paper. We'll be using a water bath and Bunsen burner. And we have chemicals: ethanol, methanol, isopropyl and butyl alcohols, acetic acid, sodium salicylate or salicylic acid can be used, acidified potassium dichromate, acidified potassium permanganate. Now these two are oxidizing agent. Alkaline potassium permanganate, again, that can be used as an oxidizing agent, and sodium carbonate. So these are the chemicals we'll be using. Now students, when we are carrying out this experiment, we'll be using these alcohols, and methanol, ethanol and 1-butanol are primary aliphatic alcohols. All three of them are primary aliphatic alcohols. But apart from them, we'll be using benzyl alcohol as well. As you can see, we have a benzene ring in this particular alcohol, making it an primary aromatic alcohol. Primary aromatic alcohol. So we'll be using all four of these alcohols in our experiment today. So we are going to first test the water solubility of each of these alcohols. So we are going to take a little bit of the alcohol and we are going to mix it with water, and we are going to observe whether the two layers or two liquids we are adding is going to be miscible in one another. Whether the alcohol and the water is miscible is what we are going to be observing here. Now, as you know, polar substances will dissolve in polar solvents. Non-polar substances will dissolve in non-polar solvents. So, while keeping that in mind, we are going to observe whether alcohols will dissolve in water. So, when you mix methyl alcohol, also referred to, actually methyl alcohol is a common name. The proper IUPAC name would be methanol. So, when you mix methanol with water, you do not see separate layers. There is no layer separation. No layer separation. This is because methanol dissolves in water due to the formation of hydrogen bonds between them. Methanol can dissolve in water in any ratio. So students, methanol has this OH group, so the O and hydrogen bond is going to be polarized, and water also has water molecules. Basically, water molecules are polar molecules, also can be forming hydrogen bonds with the OH group seen in methanol. So therefore students, they are going to dissolve in water due to the formation of hydrogen bonds. Now keep in mind, alcohols have an alkyl group as well. In this case, this methyl group is an alkyl group, which happens to be nonpolar. But this nonpolar group is very small, and the OH group is a polar group, and polarity of this particular group, as you may know, is somewhat high. And as you know, hydrogen bonds that are formed are usually a stronger type of intermolecular force. So over here, methanol is going to easily dissolve in water, and it will dissolve in water in any ratio because of the formation of hydrogen bonds between methanol and water. As you can see here, the water molecules have these OH groups which are going to be polarized, And if I just quickly remind you why these hydrogen bonds are usually quite strong, oxygen is the second most electronegative element in the periodic table, and hydrogen is not very electronegative. So there will be huge electronegativity difference between the two, causing the polarization of the bond, which will give a large partial positive charge on hydrogen and which will form a large partial negative charge on oxygen. So over here in both of these OH bonds, there's going to be considerably large partial positive and negative charges. So when this hydrogen with a large partial positive charge gets attracted to the oxygen of the ethanol, in this case methanol, what you form here is a very strong hydrogen bond. So these strong hydrogen bonds aids in dissolving of methanol in water. When considering water molecules, the OH bond is polarized. OH bond is polarized. When considering the OH bond in alcohol, that bond is also polarized due to the high electronegativity of oxygen. This aids in the formation of hydrogen bonds between the two molecules, which allows the methanol to be soluble in water. So students, this is the reason why methanol is soluble in water. What about ethanol? Will ethanol be soluble in water? The answer is yes. If you add ethanol and water together, you will not see two distinct layers being formed. You do not see a layer separation. There's only going to be one layer. That means the two liquids were able to mix with one another or dissolve in one another. So there will be no layer separation. When ethanol is mixed with water, layer separation is not observed. This is due to the formation of hydrogen bonds with water as mentioned in the case of methanol. Ethanol and water are miscible in any proportion or in any ratio. They are going to be miscible in any ratio. So the explanation is the same for ethanol and methanol both. But what about 1-butanol? What happens when 1-butanol is added to water? So let's take a look at the heading here. Butan-1-ol, or you can write the name as 1-butanol as well. So you can write this one over here or in front of the name as well. So what happens if you take 1 cubic centimeters of butan-1-ol and add water to it? So let's read the paragraph that is here. When 1-butanol is mixed with water, a layer separation is observed. Since butan-1-ol, 1-butanol, also contains an OH group, there will be hydrogen bonds formed between alcohol and water. So the formation of hydrogen bonds happens here as well, students. Because you can see even 1-butanol has this OH group. And of course, whenever OH groups are present in alcohols, those OH part of the alcohol can start to form a hydrogen bond with water. However, the hydrocarbon chain of alcohol is considerably long and is non-polar. The non-polar hydrocarbon section is also referred to as the hydrophobic section of the alcohol and is less soluble in water. Since the non-polar hydrocarbon section of butan-1-ol is larger than the non-polar hydrocarbon sections of methanol and ethanol, the solubility of the butan-1-ol is low and therefore layer separation can be observed. So students, as I mentioned earlier, alcohols contain a hydrocarbon section, or we can also say an alkyl group. So this our main hydrocarbon chain, the hydrocarbon section, when it becomes larger and larger, the solubility of alcohols go down. Why is this? Now, alcohols are mainly soluble in water thanks to the OH group present in them. OH group is capable of forming hydrogen bonds with polar solvents, actually hydrogen bonds with water, not other solvents when it comes to other solvents, if you talk about any other polar solvents, they'll be dissolving in water due to the formation of dipole interactions. But when it comes to water specifically, alcohols are soluble in water due to the formation of hydrogen bonds. So when it comes to any alcohol, the OH group is capable of forming hydrogen bonds with water. However, there is a carbon chain as well. The carbon chain, the hydrocarbon chain, is going to be nonpolar. So as we go down the homologous series of alcohols, monohydric alcohols, you're going to observe the carbon chain length increases. And the carbon chain is nonpolar. So nonpolar group length increases. So that means solubility of the alcohol goes down, because as the carbon chain's length increases, the nonpolar nature of the molecule is going to be greater than the polar nature of the molecule. So because of that, students, the molecule is mainly going to be nonpolar at one point. Although there is an OH group, that OH group will be quite small, proportional to the hydrocarbon chain's length. So students, because of that, butane 1-ol. Now butane 1-ol has 4 carbon atom long carbon chain. So at this point, this particular carbon chain is considerably long and is going to be more hydrophobic. Because of that, the solubility of butane 1-ol is going to be less than the solubilities of methanol and ethanol. And even propanol is soluble in water, but the layer separation can be observed very clearly for butane 1-ol. And we have an aromatic group when it comes to benzyl alcohols. So of course, when you have a really large aromatic ring, benzene ring here, the solubility of alcohols like this is going to be further going down, and therefore you will not be able to observe these alcohols fully dissolving in water. They are definitely going to separate into 2 distinct layers. So when 1 cubic centimeters of benzyl alcohol is mixed with water, a layer separation is observed. A layer separation is observed. As you can see, the 2 layers are formed, and benzyl alcohol is denser than water. So therefore, the benzyl alcohol layer is going to sink to the bottom. Right, so over here, again, the OH group of the alcohol is polar, or the bond is polarized, and it can form hydrogen bonds with water. However, the aromatic ring and this CH2 group over here is not polar. That is non-polar. So compared to this very small polar section of the molecule, the non-polar section of the molecule is large. And non-polar section is hydrophobic. That means it does not dissolve in water. So the section of the molecule that will not contribute to dissolving it in water is larger. So since the non-polar section of the molecule is larger, the molecule is not going to be dissolving in water. So as you can see, the density of benzyl alcohol is greater than water. Water is 1.0 grams per cubic centimeter. Here this is slightly greater than water's density. As observed in alcohols, the OH group can form hydrogen bonds with water. However, the benzene ring found in benzyl alcohol, the benzene ring found in benzyl alcohol is a large non-polar hydrophobic group, which will significantly lower the solubility of benzyl alcohol in water. This will lead to layer separation. So if you compare alcohols CH3 groups or the carbon chains over here, as you go down the homologous series of alcohols, as the carbon chain length increases, the solubility of those alcohols go down. So that is something you should keep in mind. Important observations. Alcohols with lower molecular masses easily dissolve in water. However, as you move down the homologous series of alcohols, so when I say the homologous series of alcohols, we are mainly considering the homologous series of monohydric alcohols. The alkyl groups become significantly larger compared to the OH group. This causes alcohols with larger molecular masses to be less soluble in water. So we can observe that here. So we have a homologous series of monohydric alcohols here. You can see as you move down, we keep on adding a new CH2 part to the molecule. This is CH3OH, CH3CH2OH, and you can see a new CH2 group is added each time. Now students, when you compare all of these alcohols, we can see methanol is soluble in water in any ratio. When it comes to ethanol, we can say the same. Even propanol, we can say the same. So up to having 3 carbon atoms, the solubility of alcohols in water is high. But when you have 4 carbon atoms or greater in alcohols, you can see the solubility starts to decrease. Now the solubility of alcohols have come down. So when it comes to butane 1-ol, the solubility is 7.9 grams per 100 grams of water. That is quite small. And when it comes to talking about pentane 1-ol, so at that point you can see the solubility is further decreased, only 2.3 grams per 100 grams of water. So students, as you can see, when this CH or hydrocarbon group increases in length, or when the hydrocarbon group is becoming larger and larger, since hydrocarbon group is nonpolar, solubility of the alcohol in water will decrease. Now students, in the previous part, we observed the solubilities of different alcohols, and here in this part we are going to observe the acidity or the basicity of alcohols. We are going to test whether alcohols are acidic or basic with the use of litmus paper. In this test, we will test whether there will be a color change. When wet red and blue litmus is introduced to each of the following alcohols that we mentioned earlier. So you will observe no change actually. When you add litmus paper to any of the alcohols, you will not observe any change in either blue or red litmus paper, and that means alcohols are neutral in nature. So if you take a small sample of alcohol, and if you take a red litmus paper or a blue litmus paper and insert the red or the blue litmus paper in the alcohol, or alternatively you can actually take a dropper and take a drop of alcohol and put it on to a wet litmus paper. So whenever you carry out this experiment, they are going to observe that the litmus paper will not change its color. Litmus paper, if you have taken a red litmus paper, the red litmus paper will remain red. If you have taken a blue litmus paper, the blue litmus paper will remain blue. So this is because students, the alcohols that we have over here are not acidic or not basic. They are going to be neutral in nature. So we have here ROH, meaning alcohols. So when you test alcohols with red litmus paper or blue litmus paper, you will observe no change, right? So you have wet red litmus paper. So if you add wet red litmus paper to alcohols, as I mentioned earlier, the litmus paper will remain red. And when you test the alcohol with wet blue litmus paper, again, wet blue litmus paper will not change its color, it will remain blue. Reactions that are associated with breaking off the OH bond. So this is another very important part of alcohols that we have to look into. Alcohols can act as an acid. It can act as an acid when reacted with a reactive metal like sodium or other alkaline metals. Now, there's a very big difference when it comes to saying alcohols are neutral in nature. When it comes to alcohols being added to water, you will not observe any acidity or any basicity. It's going to form a neutral solution. And when we say alcohols can act as acids. So when I say alcohols can act as acids, under certain conditions, it can release a hydrogen and act as an acid. So one such instance is when alcohols are reacted with a very reactive metal. Alcohols on their own will not usually release a hydrogen. However, if it is reacted with something very reactive like the group 1 elements, then they will react with them to release NH+. When the reaction takes place, an alkoxide anion and hydrogen gas will be produced. Alkoxide ions are known to be strong nucleophiles as well as strong bases. So you can see, students, usually alcohols, especially in water, will not automatically release NH+, because water is not reactive enough for the alcohol to release NH+. But if a very reactive element like sodium or potassium is introduced to the alcohol, at that point, sodium is capable of making this alcohol release the hydrogen attached to the oxygen. So at that point, what you form over here is referred to as an alkoxide ion, and we have the sodium ion here. So what we have formed here is sodium alkoxide. And apart from that, hydrogen gas will be formed. Due to the polarization of the OH bond, alcohols can display acidic properties. However, acidic properties seen in alcohol is not sufficient to show reactions with sodium hydroxide or sodium carbonate. So, although we say alcohols can act as an acid, first of all, alcohols can act as an acid due to the polarization of the oxygen-hydrogen bonds seen in alcohols. However, alcohols cannot easily release this hydrogen. Alcohols cannot easily release the hydrogen. Alcohols will release the hydrogen in the presence of only very reactive substances like group 1 elements like sodium. Sodium is extremely reactive. So at that point, when sodium is introduced in alcohol, sodium is capable of making the alcohol remove the H and form the alkoxide ion, and hydrogen gas will be produced. However, sodium hydroxide or sodium carbonate, when it is added to an alcohol, alcohol's acidity is not sufficient enough to show any reaction with either sodium hydroxide or sodium carbonate. In the presence of sodium hydroxide or sodium carbonate, alcohols are not going to be able to react and produce hydrogen gas and alkoxide. So one thing to keep in mind is that in the presence of sodium hydroxide or sodium carbonate, alcohols will not be able to react with them and produce the alkoxide ions. So one thing to keep in mind is, although alcohols react with sodium, it will not show any reactions with any of the bases mentioned here. Sodium hydroxide is a strong base. Sodium carbonate is a weak base. It will not show any reactions with any of these sodium hydroxide or sodium carbonate bases. It will only show reactions with very reactive species like group 1 elements. Reactions with sodium carbonate. So just to see if there are any reactions, we can add sodium carbonate to an alcohol and see whether we are going to observe any changes. So alcohol and sodium carbonate, if they added together, you will observe no change. No change. But earlier we saw when sodium and alcohol is added together, you can have a very clear observation actually. Hydrogen gas is produced. So if you take a test tube and add a piece of sodium, you can observe the formation of a gas, and sodium will also react vigorously. So we can get an idea that there is a reaction taking place. Over here, when you add these two together, you don't observe any change. Sodium carbonate is considered to be a fairly strong base in aqueous medium. When it is reacted with alcohols, there won't be a reaction, as alcohols are not sufficiently strong acids to show a reaction with sodium carbonate. Here, alcohols act as a neutral compound. Now students, I hope you remember when we are testing for acidity of substances, one of the tests that we do is we take these sodium hydroxide and sodium carbonate and see whether these acids that we are dealing with can react with them. So usually strong acids or acids with considerable acidity are capable of reacting with all three. Especially with sodium hydroxide, only acids that have a considerable acidity will be reacting. For example, if you take alcohols, phenols and carboxylic acids, carboxylic acids are going to be the most acidic out of the three. Then comes phenols, and then our least acidic will be alcohols. So alcohols will only be able to react with sodium. It will not be able to react with sodium hydroxide or sodium carbonate. Right? So if you take a look at, now before we move on to acids, if you take a look at the reactivity or how strongly reactive each of these other reagents are, sodium is very reactive. And then comes a very strong base, sodium hydroxide, that is also quite reactive. And then out of the lot, we can argue that the least reactive out of the three options given would be sodium carbonate. So when we are trying to find out the acidity or how strongly acidic each of the acids that I mentioned are based on whether or not acid can react with a slightly less strong base, we can determine whether that particular acid is a strong acid or a weak acid. So like I mentioned earlier, alcohols are quite weak acids. They can only react with sodium. When it comes to phenols, phenols can react with sodium as well as sodium hydroxide. It will not show reactions with sodium carbonate. So the acidity of phenol is not sufficient to show a reaction with sodium carbonate. However, carboxylic acids are sufficiently acidic to react with sodium, sodium hydroxide and sodium carbonate. Right students, so we can see when it comes to alcohols very clearly, it does not show a reaction with sodium carbonate. So in this case, we can say in this particular experiment, alcohols have acted as a neutral compound. So over here, we have a small observation made. No matter what the alcohol is, you do not see any reaction with sodium hydroxide or sodium carbonate. So any of these alcohols will not show any reaction with sodium hydroxide or sodium carbonate. But all of them will show reactions with sodium. Now we move on to the fourth part, the reaction between alcohols and carboxylic acids. Now this results in formation of esters due to the acylation of alcohols. When alcohols are reacted with carboxylic acids, esters are formed. This is an esterification reaction. Here, concentrated sulfuric acid is used as a catalyst. In this reaction, the OH bond of the alcohol will be broken. Now, over here students, in this part, what you have over here can be referred to as an acyl group. So you have this section joined to the alcohol when you are carrying out this esterification reaction. So we can say the alcohol is going to be, this is referred to as a acylation of alcohols. This is referred to as a acylation of alcohols. So also another name given for this particular reaction is going to be an esterification reaction. The reason why we call this an esterification reaction is at the end of this reaction, the main product that is formed is the ester. So when you're carrying out this reaction, you can see we have given here a general formula of carboxylic acids. Carboxylic acids have the functional group COOH. So the OH group of the carboxylic acid will be removed along with the hydrogen of the alcohol. So OH and hydrogen together will form water. And the RO section of the alcohol will attach itself to RCOO, or actually C double bonded oxygen part of the carboxylic acid. So when these two parts join together, what you form here is an ester. Esters are volatile compounds and have a very characteristic odor. Very characteristic smell will be there. Actually, when you are conducting this experiment in the lab, you will observe that the entire lab is filled with a very pleasant odor, usually a fruity odor, but based on the ester you have formed, you might get different odors as well. However, majority of the esters that we usually going to be having a fruity or a floral aroma. So some of the esters that we form are listed here along with their smells. So one of the esters that we can form in the lab is methyl salicylate. So methyl salicylate has this wintergreen smell. This is the smell that you observe when you use Wintergino, right? When you are having a muscle pain, you use ointment referred to as Wintergino. The smell of this is basically going to be the wintergreen smell. So you are somewhat familiar with this wintergreen smell because you may have come across Wintergino. And we have alcohol. So we have this methanol or methyl alcohol that is reacted with salicylic acid. So salicylic acid will react with methanol in the presence of concentrated sulfuric acid and heat, and will produce methyl salicylate, which will have this wintergreen smell. And then we have benzyl acetate. So benzyl acetate structure is given here. It has a floral aroma. It actually smells very much like jasmine. So jasmine or floral aroma will be observed when you form benzyl acetate. And to produce benzyl acetate, we would need benzyl alcohol, and we also need acetic acid. So what you form is benzyl acetate. And students, apart from that, we have ethyl acetate here. Ethyl acetate smells like the pear fruit. So it will, the entire lab, if you have produced sufficient amount of this ester, will smell like pears. So the pear fruit smell is seen in ethyl acetate. So to produce this, we will need ethanol, or also known as ethyl alcohol, and acetic acid, also known as ethanoic acid. Actually, ethyl acetate is a common name. Ethyl acetate is a common name. The IUPAC name of this would be ethyl ethanoate. ethyl ethanoate. And students, we then have butyl acetate. Butyl acetate, again, it will be a very fruity odor, very close to the smell of apples. To produce this butyl acetate, we will need butyl alcohol, also known as butane 1-ol, and acetic acid, again also known as ethanoic acid. So what you form here has the IUPAC name butyl ethanoate. Butyl ethanoate. Here we use the common name butyl acetate, but the IUPAC name would be butyl ethanoate. Again, we have some other examples here. So you can go through the names here, students. So names and different types of smells that you observe here. We have butyl salicylate, odor of grapes. So butyl salicylate smells like grapes. So you need salicylic acid and butyl alcohol to produce this. And when you use pentyl alcohol or pentanol or pentan 1-ol and acetic acid, you will form pentyl acetate, which has the smell of bananas. And then when it comes to octyl acetate, it has the odor of orange fruit. So you will need octyl alcohol, right? So there are altogether 8 carbon atoms in the main carbon chain. And you'll be using acetic acid. So this alcohol along with the acid will form octyl acetate, which has the smell of the orange fruit. And finally, we have ethyl propanoate, which is going to be formed when propanoic acid is reacted with ethyl alcohol in the presence of the catalyst concentrated sulfuric acid. And the smell of this substance is going to be the smell of pineapples, or we say odor of the pineapple fruit. So now we have looked at a few esters, and we see majority of them do have fruity odors, right? Majority of them have fruity odors. There are 2 esters that we discussed that did not have a fruity odor, but majority of them smells like fruit. Then we move on to the next part, where we observe the reactions that are taking place between the alcohols in producing these esters. So you have here our ethanoic acid, also known as acetic acid. So when ethanoic acid or acetic acid is reacted with methanol, also referred to as methyl alcohol, you will form methyl acetate, or IUPAC name would be methyl ethanoate. So students, apart from that, you will be forming water as well. As you see, a hydrogen from the alcohol along with the OH in the carboxylic acid will be removed as a water molecule, right? So, and then the CH3O part of the alcohol will join with this carbon oxygen double bond carbon here, and you will form the ester that way. So the link that is formed here can also be referred to as an ester bond or ester linkage. When the formed ester is added to cool water, a characteristic nail varnish or nail polish remover smell would be observed. So students, the smell that is associated with this particular ester, which is methyl ethanoate or methyl acetate, is going to be the smell of nail polish remover. And then we have ethanoic acid reacted with ethanol, and when they react, they will form ethyl ethanoate, or in other words, ethyl acetate. So this ethyl acetate is going to be formed when you carry out the same reaction we carried out earlier. One thing to notice is, instead of always using the carboxylic acid to carry out these esterifications with the use of alcohol, instead of using the carboxylic acid, we can use a derivative of carboxylic acid, which are acyl chlorides. Actually, students, acyl chlorides are more reactive. Acyl chlorides are more reactive than carboxylic acids. So you would not need certain conditions that we employ here, like heat, when we are carrying out the esterifications reactions with the use of acyl chloride. Acyl chloride is more reactive than carboxylic acid. So instead of using the carboxylic acid, we can carry out the reaction the following way as well. You can take ethanol chloride. This is the acyl chloride. Instead of using the carboxylic acid, we can use ethanol chloride, which is the replacement for this acid we have used here. And then we have ethanol, CH3, CH2, OH. So when you react them together, the product would be the same. Product is CH3, the ester would be the same. CH3, C double bonded O, and O, CH2, CH3. So product is the same. You always name the alkyl group that is connected to directly oxygen first. So this alkyl group's name is ethyl, and then we name the carbon chain that is connected to the carbon oxygen double bond, right? So here there are two carbons and the name is going to be ethanoate, right? The ending of the esters are going to be OAte. So the full name here, according to the IUPAC's naming system, is going to be ethyl ethanoate. Ethyl ethanoate. All right, students. So after, the common name would be again ethyl. This group is also referred to as the acetate group because it comes from the acetic acid. So the common name would be ethyl acetate. Apart from that, now that is the main product, the ester that is formed. Apart from that, you can see here in the alcohol, this hydrogen will be removed along with this Cl. So you will see HCl being produced as well. You will see HCl being produced as well. Keep in mind there is a mechanism in which these products are formed, through which these products are formed. So it is not just that H and Cl gets together and form HCl. There is a more complex mechanism we'll be observing in a second. The reaction type that is observed in the above reaction is nucleophilic substitution. Alcohol will act as a nucleophile. So the reaction mechanism is nucleophilic substitution, and the nucleophile observed here in these reactions are going to be the alcohol. So let's observe the mechanism. So you can see over here we have the carboxylic acid, and the carboxylic acid carbon, students, this carbon over here is not neutral. It has a partial charge on it. You can see the carboxylic acid carbon on both ends is connected to oxygen atoms. So if you mainly consider the carbon oxygen double bond, we can write this particular oxygen is partially, we'll use a different color, partially negatively charged, as oxygens are electronegative than carbons. So therefore carbon over here is partially positive charged. So what does that mean? Now students, if you have a partial positive charge on an atom, that means the electron density around that atom has gone down. So in this case, the carbon's electron density is less. That is why it is carrying a partial positive charge. So nucleophiles can attack these types of electron deficient species. So now the carbon over here that we have highlighted is a carbon that is susceptible to an attack from a nucleophile. So nucleophiles are electron-rich species. Electron-deficient groups are going to react with nucleophiles. Nucleophiles are electron-rich. Electrophiles are electron-poor or electron-deficient. So students, over here we have a nucleophile. The alcohol that we have is a nucleophile. So we have this nucleophile initiating an attack and attacking the carbon which is somewhat electron deficient. So one of the reasons why oxygen over here in alcohol is capable of acting as a nucleophile is oxygen has two lone pairs. Although we have indicated one here, oxygen actually have two lone pairs of electrons there. So a lone pair can be donated to form a bond between the oxygen and the carbon here. So carbon can't form 5 bonds. So at that point, the pi bond, which is a weaker bond compared to the sigma bonds, will break. So carbon oxygen double bond contains one sigma bond and a pi bond, and all the other bonds around carbon are sigma bonds. So the carbon oxygen pi bond will break, and the electrons pertaining to that bond will be given to the oxygen atom here, as indicated above. So when that happens, that particular oxygen will become minus or negative in charge. So now you can see the oxygen of the alcohol is directly attached to the carbon. So at that point, students, the oxygen is positively charged. And why is this? Because we saw to form this oxygen-carbon bond, both the electrons were provided by oxygen. Normally, when a covalent bond is formed, only one electron is provided by any atom. However, oxygen has provided both the electrons, meaning oxygen has provided one electron extra from the oxygen atom. So now oxygen has lost an electron in the forming of this bond. So therefore, due to the losing of that electron, oxygen is going to be +1 in charge. So having a +1 charge on a very electronegative element like oxygen is not very stable. So this oxygen-hydrogen bond, which is already quite polarized. As you know, oxygen is very electronegative, so this bond is quite polarized. So this bond easily will break, and the electrons pertaining to that bond will be given to the oxygen atom. And students, here keep in mind, although there are 2 electrons in this bond, 1 electron initially came from oxygen, 1 electron came from hydrogen. So when both electrons are given, oxygen only gains 1 additional electron, which is the electron of hydrogen. So therefore, when these bond electrons are given to oxygen, only thing that is going to happen is the neutralization of the positive charge. There won't be a gaining of a negative charge here, because although the 2 electrons are coming here, 1 electron was already oxygen's, only 1 additional electron comes to oxygen through the bond. So after that, you will form this intermediary compound. So this is an intermediate, right? And you can see the H plus in the medium can gain these 2 electrons to form the OH bond here, right? And then this intermediate can undergo the change to produce our final ester molecule. Actually, a hydrogen here along with the OH group here can form a water molecule, right? And can form the ester molecule. In this case, we are forming ethyl ethanoate, which has the order of the pair fruit. So this is the mechanism for the reaction between carboxylic acids and alcohols. So what is the type of mechanism we see here? The reaction was initiated by a nucleophile. Nucleophile initiated the reaction. We can also say nucleophile initiated the attack. So this is a nucleophilic reaction because of that. And what has happened? The OH group, this group was substituted by the OR or OCH2CH3, this group. So earlier on, instead of this CH2CH3 group, we had an OH group here. This OH group went away, right, as you can see, and the OR group, OR in the sense alcohol, R group along with the oxygen of alcohol will come and attach itself to this carbon. Right, so because of that, students, what has happened here is a substitution of the OH group. OH group will go away, another group will come and attach here. So because of that, this is not an addition reaction. This is referred to as a nucleophilic substitution reaction. So there are two parts to the name. Nucleophilic refers to the fact that nucleophile initiates a reaction, and substitution means there was an initial group that was replaced by a different group. So because of that, this is referred to as a substitution reaction. So the full mechanism is a nucleophilic substitution reaction. Again, we can observe other reactions that take place as well. You can very clearly see here, if you react ethanoic acid with butane-1-ol, right, or butyl alcohol, you will form, you can see the OH part. The OH section here will be removed, and the hydrogen from the alcohol will be removed, and those together will form the water molecule, and the O, CH2, 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 CH3 part will get connected to this carbon over here, forming our butyl acetate or butyl ethanoate, butyl acetate, or also referred to as butyl ethanoate. Butyl ethanoate ester. And you can also carry out salicylic acid and methanol reaction. You can see, again, we use the same conditions, conc H2SO4 and heat. Here also, methanol, the alcohol will lose only the hydrogen, but the carboxylic acid will lose the OH group. And together they will form the water, and the OCH3 group will attach itself to the CO or carbon. So then you form this. This is referred to as methyl salicylate. Methyl salicylate. So this formation of methyl salicylate can be used specifically to identify the presence of methanol, or this can also be used to identify the salicylic acid as well. So if you form methyl salicylate, you will feel the very characteristic winter green smell. Methyl salicylate has this very characteristic winter green smell. So once you react, you will form this ester methyl salicylate, and methyl salicylate will have a very strong, very characteristic winter green smell that confirms the production of this particular ester. So if you add ethanol and sulfuric acid to an unknown carboxylic acid and carry out the esterification reaction, towards the end of that, if you produce a winter green smell, that means the acid that was present in the test tube was salicylic acid. You can carry out the reverse version of this experiment as well. If you take, let's say, an unknown alcohol, and to it if you add salicylic acid along with the sulfuric acid and heat it, and towards the end of the reaction, if you observe a very strong winter green smell, that means what you have taken into the test tube is the methyl alcohol or methanol. Right. So students, this is how you will carry out that test. Reactions of alcohols with oxidizing agents. There are few oxidizing agents that can show reactions with alcohols. The products formed when alcohols undergo oxidation will depend on the type of alcohols. As you know, there are few different types of alcohols: primary, secondary and tertiary alcohols. So based on whether the alcohol you are working with is a primary, secondary or tertiary, the product that is produced due to oxidation of the alcohol might vary. The following can be used as oxidizing agents: acidified potassium permanganate. We remind ourselves, acidified potassium permanganate is a purple color solution. And then we have acidified potassium dichromate. Acidified potassium dichromate is an orange color solution. Both of these are good oxidizing agents. We can use acidified chromium trioxide, and we can also use alkaline potassium permanganate as well. Usually, students, we mainly use acidified potassium permanganate or acidified potassium dichromate most commonly. Apart from that, acidified chromium trioxide and alkaline potassium permanganate can also be used to carry out oxidation reactions. Oxidation of primary alcohols. Now, since there are three main types of alcohols, we will first see what happens when you try to oxidize primary alcohols. Primary alcohols can be turned into the corresponding carboxylic acid through the formation of an aldehyde with the use of acidified potassium permanganate, acidified potassium dichromate, acidified chromium trioxide. All of these can be used to carry out this particular conversion. So you can see primary alcohol is turned into carboxylic acid. Primary alcohol, students, when you react it with an oxidizing agent, will first turn into its corresponding aldehyde. But obtaining this aldehyde is not going to be that easy majority of the time. If you are carrying this reaction in a heat under reflux setup, at that point, the primary alcohol will directly turn into the carboxylic acid. So you can mainly obtain only the carboxylic acid. If you specifically want to obtain the aldehyde, there are certain measures that you can take, especially instead of using a heat under reflux setup, you can actually use a simple distillation setup to obtain the aldehyde. But in our experiments, when we carry out oxidation, especially with the use of acidified potassium permanganate or acidified potassium dichromate, when you directly introduce the alcohol and heat it under a reflux setup, at that point you are mainly going to obtain the carboxylic acid. The corresponding carboxylic acid along with chromium 3 plus or Mn2 plus will be formed. So if you use acidified potassium permanganate, when the carboxylic acid is formed, the permanganate ion, which is purple in color, will get reduced to form Mn2 plus. Mn2 plus is colorless. We say Mn2 plus in aqueous medium has a slight pink color, but the color intensity of this complex ion that is formed is going to be extremely low. Because of that, students, you don't observe that light pink color of aqueous Mn2 plus solutions. Instead, we say the color change when potassium permanganate is used is from purple to colorless. If you use potassium dichromate in acidic medium is orange in color, but if you use potassium dichromate to carry out this oxidation reaction, as potassium dichromate reduces, it will form chromium 3 plus. Now, chromium 3 plus in aqueous medium, especially if it is acidified with something like sulfuric acid, will usually appear green in color. So, chromium 3 plus aqueous ion in aqueous medium will usually appear green in color. So, students, these are the reactions that are taking place when we use acidified potassium permanganate or acidified potassium dichromate. Whenever you use either of these oxidizing agents, keep in mind the primary alcohol will first turn into the aldehyde, and aldehyde will be further oxidized to form the carboxylic acid. You can see the observations here. So if you use a primary alcohol, then if you use potassium permanganate, the purple color solution, that is our potassium permanganate, will turn to a colorless solution as Mn2 plus ions are formed when this reaction proceeds. So when it comes to alcohol, it will turn into a carboxylic acid. When it comes to permanganate ions, it will turn into Mn2 plus ions. Permanganate ions are purple in color, Mn2 plus are considered to be colorless in aqueous medium. And when it comes to our potassium dichromate oxidizing agent, if you use potassium dichromate, that is going to be orange in color. But as the reaction proceeds, the dichromate ions will get used up. They will turn into Cr3 plus ions. So Cr3 plus ions are green in color. Cr3 plus ions are green in color. So this green color Cr3 plus ion solutions will be an indication that the oxidation has happened and the alcohol has turned into a carboxylic acid. So these are the color changes that you observe when the reaction or when primary alcohols are oxidized. If alkaline potassium permanganate is used as the oxidizing agent, the primary alcohol will oxidize to form the salt of the corresponding carboxylic acid, not the carboxylic acid itself. Instead, the salt of the corresponding carboxylic acid will be formed, and the alkaline permanganate ions will turn into manganese dioxide. Manganese dioxide solid, MnO2 solid will be formed. Right, so students, keep in mind, in alkaline medium, permanganate ions always turn into MnO2 when oxidation is carried out. So permanganate ions are good oxidizing agents in both acidic and alkaline medium, but when permanganate ions are carrying out this oxidation reaction, they themselves get reduced. So therefore, students, in acidic medium, permanganate ions get reduced to Mn2 plus, while in alkaline medium, they get reduced to form MnO2. So in acidic medium, permanganate ions go from purple to colorless. So it's just the solutions that are formed, no precipitate. But in alkaline medium, it goes from a purple color solution to a clear solution with a brown color precipitate. So we say the purple color will be decolorized and a brown color MnO2 precipitate will be formed. So at this point, when you carry out this reaction, instead of the carboxylic acid, you will be producing the sodium salt of the carboxylic acid. Now imagine, even if you carried out this reaction to form the carboxylic acid, now the carboxylic acid produced will be present in an alkaline medium. Now carboxylic acids will react with the base, or alkaline medium contains enough and more OH minus ions. So the carboxylic acid produced will definitely react with this to produce a carboxylate anion. So what you see here is a sodium carboxylate salt. So over here, instead of having our carboxylic acid formed, the final product that you obtain is not going to be the carboxylic acid, but the sodium salt of the carboxylic acid. So if you want to obtain the carboxylic acid once more, you can separate the brown color precipitate, which happens to be MnO2, and then you can acidify the medium until you obtain our carboxylic acid. In acidic medium, you will observe that the carboxylic acid will be reformed. Observations: when in the previous step, when we were carrying out this reaction, the purple color solution will decolorize to form a brown color precipitate. And another important detail is, when preparing our alkaline potassium permanganate solution, we can make the medium alkaline with the use of sodium carbonate. So sodium carbonate can be used as a base to make the medium alkaline. Now, apart from these oxidizing agents, another very important oxidizing agent can be used. That is pyridium chlorochromate. Pyridium chlorochromate, also often abbreviated to PCC. Often we abbreviate this term to PCC And even when it comes to our conversions, you might notice that we write PCC instead of writing the whole name pyridium chlorochromate. So when PCC is used as the oxidizing agent, the alcohol will not get oxidized beyond the aldehyde state. So students, over here this oxidation happens under more controlled conditions in the presence of PCC. So therefore, the primary alcohol will not get oxidized beyond the aldehyde. That means it will not get oxidized all the way to the carboxylic acid. So if you want to stop the oxidation at aldehyde, you can use pyridium chlorochromate, also often abbreviated to PCC. So if you use a primary alcohol and oxidize the primary alcohol in the presence of PCC, you will only produce its corresponding aldehyde. And then we move on to oxidation of secondary alcohols. Now, secondary alcohols will get oxidized to form ketones, very important. Secondary alcohols will get oxidized to form ketones. So if you take a sample of secondary alcohols, you can see in a secondary alcohol we have the carbon bearing, the OH group has two alkyl groups. And when you add potassium dichromate in acidic medium, the reaction mixture is going to appear orange in color initially, but as the reaction proceeds, the dichromate ions that are orange in color will turn into chromium 3 plus ions in aqueous medium, which happens to give off a green color. And the organic product that is formed is a ketone. So secondary alcohols turn into ketones upon oxidation with acidified potassium permanganate or acidified potassium dichromate. So that example is given here as well. You can see we can use acidified potassium permanganate. The permanganate solution will be purple, or if you want, you can use all of these oxidizing agents as well. Acidified potassium dichromate, H plus CrO3 or PCC can be used. All of these oxidizing agents can convert the secondary alcohol into a ketone. And when you do that, you will observe the formation of the ketone along with, now if you use acidified potassium permanganate, Mn2 plus will be formed, so the color change will be from purple to colorless. If you use potassium dichromate, the color change will be from orange to green color solution. Again, over here students, you can see the same observation given here. Now in this case, we are using acidified potassium permanganate specifically to give you an idea about the color change. So earlier on this experiment, we spoke about what happens if acidified potassium dichromate was used. Here we talk about what happens when acidified potassium permanganate is used. So at that point, the color changes from purple to colorless. Mn2 plus aqueous ions will be formed. So therefore, the color changes from purple to colorless. And the secondary alcohol will turn into a ketone. What about tertiary alcohols? Can we oxidize tertiary alcohols? Tertiary alcohols will not show any reactions with any of the below oxidizing agents. So all of these oxidizing agents are not capable of oxidizing a tertiary alcohol. So if you add acidified potassium permanganate or any of these oxidizing agents, you will notice the tertiary alcohol will not get reacted. So if you use potassium permanganate solutions, the purple color will not change when you try to react it with a tertiary alcohol. The orange color of a potassium dichromate solution will not change over time when you try to react it with a tertiary alcohol. This indicates that the oxidation reaction we expect is not taking place. So you can see, if you use acidified potassium permanganate and then heat the solution along with a tertiary alcohol, after heating and trying to carry out the reaction, at the end also you still have the purple color remaining in the medium, indicating that the tertiary alcohol did not undergo an oxidation. Because if it did undergo an oxidation, then the permanganate ions will undergo a reduction, decreasing the color intensity of purple, or maybe completely turning the solution into a colorless solution. So this indicates that the tertiary alcohol did not undergo oxidation. Tertiary alcohols will not undergo oxidation under the same conditions that primary and secondary alcohols do. So tertiary alcohols will usually not undergo oxidation like primary and secondary alcohols. Oxidation of primary and secondary aromatic alcohols. So this is very important. Aromatic alcohols. Both primary and secondary aromatic alcohols will undergo oxidation in the presence of strong oxidizing agents to produce benzoic acid. Benzoic acid is water insoluble and is a white color precipitate. So students, you can see here there are two alcohols, and you can very clearly see the first one is a primary alcohol. You can see the carbon bearing the OH has two hydrogens, only one alkyl group is attached. Actually, that is also a benzene ring that is attached to that carbon. So this is aromatic alcohol. Here we have the carbon bearing the OH has two alkyl groups attached. One is aromatic ring or benzene ring, one is a CH3 group. So this is a secondary alcohol. The first one is a primary alcohol. So regardless of what type of alcohol it is, whether it's a primary or secondary, when it comes to aromatic primary or aromatic secondary alcohols, if you oxidize them, both of them will turn into benzoic acid. The benzoic acid formed here is not a water soluble substance. So primary and secondary aromatic alcohols can undergo oxidation in the presence of a strong oxidizing agent like acidified potassium permanganate, acidified potassium dichromate, and when they undergo oxidation, the aromatic alcohols will produce benzoic acid, and benzoic acid is not water soluble and it is a white color precipitate. And apart from that, if you use acidified potassium permanganate for this oxidation, like in the previous instances, permanganate ions will reduce to form Mn2+, and dichromate ions will reduce to form Cr3+. Mn2+ ion solutions will be colorless, as well as when it comes to chromium 3+, it will be green in color. So if you use potassium dichromate, the color change will be from orange to green. If you use potassium permanganate, it will be from purple to colorless. So one good example is given here, students. If you use a benzyl alcohol, you can see benzyl alcohol added with acidified potassium permanganate. You can very clearly see the formation of a white color precipitate. Here, formation of a white color precipitate will be observed, right? Majority of the time, it can also get produced like needle-like precipitate, especially benzoic acid will be produced as a needle-like precipitate. So you can see a fine white color precipitate getting formed when you're carrying out this experiment. If you use benzyl alcohol and potassium dichromate, again the same precipitate, white color precipitate will be formed. Apart from that, you will see the formation of a green color solution. Over here as well, you will see a clear colorless solution here. This solution over here is Mn2+, and solution will appear colorless. But if you use acidified potassium dichromate, you will observe a white color precipitate formed. Apart from that, you will have a supernatant or solution that is green in color, because the color change is going to be from orange to green. The orange color species is the dichromate ion, and green color species is going to be your Cr3+ ions in aqueous medium. So students, in this part, we are carrying out the oxidation reaction with the use of alkaline medium potassium permanganate. So when you carry out this reaction with the use of alkaline medium potassium permanganate, this aromatic alcohol will turn into benzoic acid, as we saw in the previous instances. Apart from that, we know when alkaline medium potassium permanganate acts as an oxidizing agent, the permanganate ions are reduced to form MnO2, manganese dioxide, which is a brown color precipitate. This brown color precipitate will be formed as fine particles of brown color precipitate. So initially they will be dispersed in the aqueous medium and make the aqueous medium appear brown in color. However, this is not a brown color solution that is formed. This medium will appear brown due to the formation of MnO2 solid in such fine particle nature. So because of that, students, due to distribution of these fine particles of MnO2 precipitate, the entire medium will appear brown in color. Apart from that, we can also see the formation of a white color precipitate, which happens to be our benzoic acid. And the brown color precipitate that is formed is MnO2, which is formed due to the reduction of permanganate ions to MnO2. So with this, students, we can conclude the theory parts that are revolving around this experiment. By now, I hope you have developed a good understanding about different types of reactions that are revolving around alcohols. So while keeping in mind what are the theory parts that we learned throughout this session, we can now move on to the lab and actually conduct these experiments and observe the different changes that happen when we carry out different experiments. So let's move on to the lab and actually conduct this experiment. GCE Advanced Level Chemistry Practical Series Experiment number 25, Examination of Properties of Alcohols. In this experiment, we aim to provide you with necessary knowledge about how the OH group in alcohols take part in different reactions. For this purpose, we are going to take alcohols and we are going to dissolve it in water and see if alcohols are soluble in water. And then we will take litmus paper and try to see if litmus paper changes color in the presence of alcohols. And then we are going to react alcohols with sodium carbonate to see if there's a reaction. We have potassium permanganate, potassium dichromate as oxidizing agents. We are going to observe how alcohols react with these oxidizing agents. And finally, we are going to react alcohols with carboxylic acids to see if we can form esters. So in this experiment, we aim to give you this knowledge about how the OH group in alcohols take part in different reactions. Now, let's move on to identifying different reagents and equipment we will be using for this practical. Students, what we have here are the reagents and the equipment we will be using for this experiment. So let's take a look at them. We will be using methanol or methyl alcohol. We have ethanol here or ethyl alcohol. We have butanol, also known as butyl alcohol. We have benzyl alcohol. We have acetic acid or ethanoic acid. We have salicylic acid over here. We have sodium carbonate. We have potassium dichromate, potassium permanganate. Over here we have bromine water, concentrated sulfuric acid, dilute sulfuric acid, and we have some distilled water here. Apart from that, we will be using some litmus paper. We have here blue litmus paper and red litmus paper. We will be using a stirrer, a test tube holder, a retort stand, and we will be using a beaker, and we will be having some water in the beaker, and we will be warming it up to use this setup as a water bath. So what you see here is a setup of a water bath we have fixed. We will be using test tubes placed on a test tube rack. So these are the main equipment and the reagents we will be using for this experiment. Now, let's move on to the first part of our experiment. Students, in the first part of our experiment, we are going to observe the solubilities of different alcohols in water. As you know, when it comes to alcohols, if you have a larger carbon chain, the solubilities of those alcohols are going to be less, and alcohols with smaller number of carbon atoms will dissolve well in water. Alcohols are made out of an alkyl group and an OH group connected to the alkyl group. An OH group is a polar group which will allow the alcohol to dissolve in a polar solvent like water. However, as the alkyl group or the carbon chain increases in length, this carbon chain is going to be non-polar. So as the carbon chain increases in length, the non-polar section of the alcohol increases in proportion. This will make the alcohol molecule more and more insoluble in water. So smaller alcohols such as methanol, ethanol, propanol will dissolve well in water. Actually, these alcohols dissolve in any ratio with water. However, alcohols with a slightly larger carbon chain such as butanol and any other alcohol after that, or especially alcohols containing a benzene ring, are not going to be very soluble in water. So we are going to observe that here in this experiment. Let's take small portions of methanol, ethanol and butanol first. So we have our methanol here. We will take a small amount of methanol into a test tube. We'll use a dropper to take a small amount of methanol into a test tube. Now students, you can observe the appearance of methanol. Methanol is a clear liquid. It does not have a color. It is a clear liquid. We'll close the methanol bottle. And we will now add a small amount of distilled water. Since methanol is a very small alcohol or alcohol with only one carbon atom, methanol should dissolve fairly easily with water. And as you can see, when you add water, there was no layer separation. When you add water to methanol, there was no layer separation, as methanol is capable of mixing well with water in any ratio. So therefore, what you see here is a mix of methanol and water, and we did not observe a layer separation, indicating that methanol is soluble in water. Methanol is quite soluble in water. Now we will move on to ethanol. We have here our ethanol. We'll take a dropper and take a small amount of ethanol into another test tube. Now students, you can observe the appearance of ethanol as well. A clear liquid, again no specific color that can be observed. So ethanol is a clear liquid. As you know, ethanol also is a small alcohol, it's a primary alcohol, and it dissolves really well in water. As I mentioned earlier, alcohols with a small number of carbon atoms in the carbon chain tend to dissolve really well in water. This one has only 2 carbon atoms. Ethanol has only 2 carbon atoms in it, so therefore this alcohol dissolves really well in water. If you take a small amount of distilled water and try to dissolve this ethanol, you are going to observe that the ethanol mixes well with water. You can see there is no layer separation. There is no layer separation. This indicates that ethanol is soluble in water. Then we move on to butanol. Now students, butanol has a bit of a larger alkyl group. It is containing a carbon chain made of 4 carbon atoms. So when it comes to an alcohol, you have the carbon chain and the OH group, which is the polar group, and the carbon chain is going to be non-polar. And the non-polar group is the reason why alcohols tend to be a bit insoluble in water, as they have a longer or a larger carbon chain. So butanol has a bit of a larger carbon chain, so we can expect it to not dissolve very well in water. Solubility of butanol should be somewhat lower than the solubilities of methanol and ethanol. So let's take our butanol and we'll take a dropper and take some butanol into a test tube like this. As you can see students, when it comes to butanol also, it's a clear liquid. You do not see any cloudy nature here, and you do not see a color. Butanol is a clear liquid. And to this, we are going to add some water. And as we add water, we can see if butanol is soluble in water. As you can see here, students, butanol and water form 2 layers. Butanol and water form 2 layers. They are not very soluble in one another. Butanol, like I mentioned earlier, has a larger carbon chain and has become less soluble in water compared to other alcohols that has a low number of carbon chains, such as methanol, ethanol, and propanol. Butanol, however, has started to show somewhat of an insolubility in water. Actually, the solubility of butanol is ranging around 7 to 8 grams per 100 milliliters of water. So it has actually gone down compared to the alcohols that have a low number of carbon atoms in their carbon chains. So we'll give it a mix to see if this dissolves when mixed like this. Even when mixed, you can observe they are still forming 2 layers. There are small droplets of butanol formed, but after a while these droplets will get together and will form the butanol layer. A small portion of butanol might get dissolved, as butanol has small solubility in water. Like I mentioned earlier, it ranges from around 7 to 8 grams per 100 milliliters. However, butanol is not going to be as soluble as the alcohols we observed earlier. So you can see a layer separation here. Now students, we move on to another alcohol. Now this alcohol has an aromatic group in it. This alcohol is benzyl alcohol. Obviously students, when you have an aromatic group in it, it has a large carbon chain. And we can be very sure that this is not going to be very soluble in water. In fact, the solubility of benzyl alcohol in water is around 4 grams per 100 milliliters of water. So it is somewhat low compared to all the other alcohols we observed in this experiment. So let's take a dropper and take a small amount of benzyl alcohol into a test tube. As you can see students, benzyl alcohol is also a clear liquid, has a slight yellowish hue to it. However, it's a clear liquid. And to this, we will be adding some distilled water. And as I add distilled water, please observe the layer separation. Now, you can see since benzyl alcohol has a higher density, it has sunk to the bottom, and we have our water layer on top of the benzyl alcohol layer. And one of the main observations here should be the fact that these two layers did not get mixed. These two layers did not get mixed in one another because, as I mentioned earlier, as you have a larger and a larger carbon chain in alcohols, their solubilities start to decrease. As the carbon number in or carbon atom number in alcohol increase, then the solubility of those alcohols will start to decrease. This is a good example of that. We have benzyl alcohol with an aromatic ring, or we have benzene ring here, and due to the high number of carbon atoms in this alcohol, or due to the large portion of the non-polar groups present in this alcohol is not going to be very soluble in water. I mentioned when it comes to benzyl alcohols, around 4 grams for 100 milliliters will be the solubility of these alcohols. So now let's mix it well and see if it mixes well when we shake it like this. If you observe, after attempting to mix it, droplets were formed and they were again connecting with one another to form one single benzyl alcohol layer. But you can see there's a slight turbidity in the aqueous layer. This is due to small amount of benzyl alcohol attempting to dissolve in the water layer. However, if you leave it for a while, you will see the water layer clears out and you will observe the benzyl alcohol layer separately. So students, this indicates that when alcohol's carbon chain increases in length, or if you have an alcohol with a larger carbon chain or aromatic ring attached to it, the solubilities of those alcohols will decrease. Alcohols containing a very small carbon chain, such as methanol, ethanol, and propanol, will dissolve in water in any proportion, in any ratio. However, as you increase the length of the carbon chain, their solubilities start to decrease. So alcohols with larger carbon chains will have a very low solubility in water, to the point that some of the alcohols are going to be insoluble in water. So that was the main observation when it comes to the first part of our experiment. Now students, as a summary, we observed when it comes to methanol being mixed with water, methanol and water did not form two layers. They dissolve in water in any ratio. So methanol is very soluble in water. And then we moved on to ethanol. When ethanol was dissolved in water, we saw ethanol also did not have any problem when it comes to dissolving in water. Ethanol and water did not form two layers, indicating that ethanol is also very soluble in water. In fact, ethanol and water will mix in any ratio. Then we looked at 1-butanol or butan-1-ol and water. So you can see butanol and water forms two layers, indicating the solubility of butanol was lower than the other alcohols that we observed so far. Actually, the solubility of butanol is ranging from 7 to 8 grams per 100 milliliters of water. So solubility of butanol is very, very low. And then we observed benzyl alcohols. Again, benzyl alcohol is somewhat insoluble in water. You can see the formation of two layers. Benzyl alcohol is even more insoluble compared to 1-butanol. As benzyl alcohol contains a larger carbon chain, it has become more insoluble in water. Actually, the solubility of benzyl alcohol in water ranges somewhere around 4 grams per 100 milliliters of water. In summary, as the carbon chain's length increase in an alcohol molecule, their solubility in water will decrease. Students, in this part of our experiment, we are going to observe whether litmus paper is going to show a color change when added with an alcohol. So we are going to be using 4 alcohols we used earlier in the previous part of our experiment as well. We have methanol, ethanol, 1-butanol and benzyl alcohol. Now students, in your syllabus, we study a few oxygen-containing organic compounds that show acidic properties. Those are alcohols, phenol and carboxylic acids. Alcohols show the weakest acidic properties, or alcohols are one of the weakest out of these 3 compounds that we just spoke about. When it comes to alcohols, they are quite weak in their acidic nature. They only show reactions with metallic sodium. Alcohols are not strong enough or alcohols do not show strong acidic properties to show a reaction with sodium hydroxide or sodium carbonate. When it comes to phenols, on the other hand, they are strong enough to react with metallic sodium and sodium hydroxide. However, they will not show a reaction with sodium carbonate. And then we move on to carboxylic acids. Carboxylic acids show reactions with metallic sodium, sodium hydroxide and sodium carbonate. Over here, we have litmus paper that is usually used to identify whether a medium is acidic or basic. Red litmus will turn blue in the presence of a basic medium. Blue litmus will turn red in the presence of an acidic medium. So we are going to add a few drops of alcohol that we have in front of us to each of these red and blue litmus papers. We have here a setup where we have a red and a blue litmus paper in a petri dish, and we are going to add a drop of each of these alcohols onto both a red and a blue litmus paper if we can observe a color change in them. So now we are going to add a little bit of methanol to this litmus paper. But students, before adding any alcohol to any of these litmus paper, we are going to make this litmus paper wet with a little bit of distilled water. So let's take a few drops of distilled water and we'll add distilled water to each of these litmus papers first. Now as you can see, we have made these two litmus papers wet. After that, we are going to take small amount of methanol, and we are going to add a few drops of methanol to the red litmus paper and a few drops of methanol to our blue litmus paper. As you can see, students, when we added methanol to both of these litmus papers that were made wet with water, you did not observe a color change. You did not observe red litmus paper turning to a blue color, or we did not observe the blue litmus paper turning to a red color. You can see the blue color in the blue litmus paper and the red color in the red litmus paper still persists. It did not change upon the addition of methanol. If you want to have a closer look, you'll be able to observe it here. Now, let's move on to ethanol. Before we add ethanol to our litmus paper, we have to make this litmus paper wet with distilled water. We have our distilled water here. We'll add a few drops of distilled water to red and blue litmus paper, making them wet. You can see after making them wet, they are still red and blue in color, because water that we have over here is neutral. pH of water that we have taken, distilled water here, is a neutral pH. So now we are going to take ethanol. We are going to take ethanol and we are going to add a few drops of ethanol to our litmus papers that are now made with distilled water. So I'm going to take a little bit of ethanol, and as you can see, I'm adding a few drops of ethanol to the red litmus paper, and now a few drops of ethanol to our blue litmus paper. Now students, if you observe, when we added ethanol to the red and the blue litmus paper, we did not see the color of the litmus paper changing. The color of the litmus paper remained what it was. Red litmus paper remained red and blue litmus paper remained blue. Now we will move on to 1-butanol or butyl alcohol. We have butyl alcohol here and we have our distilled water here. We will take a drop or two of distilled water and we will make our litmus papers wet with water first, and then after making our litmus papers wet with water, we can move on to adding a small amount of butanol. Now students, let's add a drop of butanol to our red litmus paper, and we will add a few drops of butanol to our blue litmus paper as well. As you can see, students, the red litmus paper and the blue litmus paper has not changed their color. Red and blue litmus paper did not change their color. This indicates that the butanol alcohol was neutral when it comes to forming an aqueous solution. So, aqueous alcohol mediums are neutral. As we saw, litmus papers did not change their color when we added alcohols onto the litmus paper. Finally, we have benzyl alcohol. Benzyl alcohol is not very soluble in water. We can directly add benzyl alcohol to see if there is going to be any change in the color of our litmus paper. As you can see, students, we do not observe a color change when it comes to adding benzyl alcohol into these litmus papers we have over here. If you really want, we can add a little bit of water as well to show that there's not going to be much of a difference when distilled water is added. So we observe when alcohols are added to litmus paper, there is no color change in the litmus paper. If the litmus paper was originally red in color, we didn't see it turning into a blue color. You saw that in these scenarios. And when it comes to blue litmus paper also, it didn't change into a red color. Although we know alcohols are acidic in nature and shows reactions with sodium, we also know the acidity of alcohols is considerably low. If you take aqueous solutions of alcohols, their pH is somewhere around pH 7, which is a neutral pH. So therefore, you will not be able to see a color change in our litmus paper. So keep in mind, students, you cannot identify the presence of an aqueous solution of alcohol with the use of litmus paper, because aqueous solutions of alcohols are going to have a neutral pH. Now, just to take it a step further to give you an understanding of what sort of color change can be expected when a strong acid and a base is reacted with pH paper, we are going to add a drop of strong acid and strong base to these sets of litmus paper we have here. Now, students, to make sure that you understand what sort of color change we should be expecting when it comes to an acidic solution and when it comes to a basic solution, when we add them to litmus paper, we are going to add a strong acid and a strong base to both red and blue litmus paper, so that you will have an understanding of what sort of color change you can expect when a medium is actually acidic and when a medium is actually basic. When it comes to using litmus paper, you have to have a good enough understanding about the color changes of litmus paper. You have to understand what type of color change will be observed when a red litmus paper is dipped in a base, or when a blue litmus paper is introduced to an acid. So to make sure that you develop that understanding, let's add small amount of acid into both red and blue litmus paper and a small amount of base to both a red and a blue litmus paper, and let's observe the color change. So we have here sodium hydroxide with us. So let's add few drops of sodium hydroxide to our red litmus paper here. You can see how the red litmus paper started changing color. It's a very prominent color change. If you add sodium hydroxide to blue litmus paper, since blue litmus paper will turn red in the presence of acids, and since we added a base, blue litmus paper didn't show a color change because blue litmus paper is normally used to identify the presence of an acid, and what we added here was a base, sodium hydroxide. So you can very clearly see when we add a base, to red and blue litmus paper, what sort of color change we are expecting. And then we have another set of red and blue litmus paper, and to this we are going to be adding dilute acid. We have sulfuric acid here. Let's add a little bit of sulfuric acid to the red litmus paper. As you can see, adding the acid to the red litmus paper did not do anything to the color of the red litmus paper. Red litmus paper remained red in color. So now let's add a small amount of this dilute acid to blue litmus paper. You can see immediately the blue litmus paper turned to a red color, right? So in the presence of an acid, what happened? The blue litmus paper showed a very clear color change to a red color. Do you see any of these blue litmus papers turn to a red color? The answer would be no. If you observe this red color in the blue litmus paper, so this used to be a blue litmus paper, now it is completely red. Do you observe a red color in any of these blue litmus papers? No. This indicates that alcohols were not acidic enough to turn the blue litmus paper into a red color. So students, with that we can conclude this part of our experiment, which is identifying whether alcohols are acidic enough to show a color change with litmus paper, and we realize alcohols are not acidic enough to show a color change with litmus paper. Litmus paper will not change their color when added with alcohols. This is due to the fact that alcohols are extremely weak acids, and aqueous solutions of alcohols are neutral in their pH. So therefore, litmus paper cannot show a color change. Now let's move on to the next part of our practical. In this part of our experiment, we are going to react sodium carbonate with the different alcohols we have in front of us. As you know, students, alcohols are acidic in nature. So when you react an acid with sodium carbonate, there will be a reaction where the carbonate ions will receive an H plus and will turn into a carbonic acid. Carbonic acid is unstable, so therefore it will decompose to produce water and carbon dioxide gas. You are going to see the formation of effervescence when you react sodium carbonate with an acid. Now, as you know, alcohols are not very acidic. So we are trying to observe here whether alcohols are capable of reacting with sodium carbonate to give carbon dioxide bubbles, or whether they are capable of reacting with sodium carbonate to produce effervescence. However, we do know for a fact that we use sodium carbonate to identify the presence of a carboxylic acid. So when you have a carboxylic acid, if you add sodium carbonate to the mix, you will see the formation of bubbles due to carboxylic acids reacting with sodium carbonate. I just want to remind you that sodium carbonate is usually used to identify the presence of a carboxylic acid. However, alcohols are quite weak when it comes to their acidic properties. So we are going to now observe if alcohols will give a reaction with sodium carbonate. So we have our sodium carbonate here, and we are going to take small samples of sodium carbonate into each of these petri dishes we have in front of us. We'll use a spatula and take small amounts of sodium carbonate into each of these petri dishes. And now, students, after taking sodium carbonate into each of these petri dishes, all that I have to do is add the alcohols that we have in front of us. We have methanol, ethanol, 1-butanol, and benzyl alcohol. So we can first take our methanol and add a few drops of methanol into our sodium carbonate. So let's take a dropper and let's take a small amount of methanol, and let's add a few drops of methanol to observe if any effervescence is produced. As you saw, when I added methanol, there was no indication of any gas being formed. So, did sodium carbonate react with methanol? According to our observation, sodium carbonate and methanol did not show us a reaction because you can't see the formation of a gas here. There was no gas produced here. So sodium carbonate and methanol did not show us a reaction. Now we can move on to ethanol. We have ethanol here. We'll take another dropper and we'll take a small amount of ethanol, and in this petri dish we have a small amount of sodium carbonate. Let's add a few drops of ethanol. Do you see formation of a gas here? Do you see any bubbles, or do you observe effervescence in this petri dish? The answer would be no. You do not see any bubbling happening here in this particular setup. So sodium carbonate and ethanol did not give us a reaction. So sodium carbonate and ethanol doesn't react with one another. This tells us that ethanol is not strong enough of an acid to react with sodium carbonate. And we can say the same about methanol. Methanol and ethanol both did not react with sodium carbonate. This indicates that they are not acidic enough, or they are not strong enough when it comes to reacting with sodium carbonate. So they are not strong in their acidic properties to show a reaction with sodium carbonate. After observing that sodium carbonate doesn't show a reaction with ethanol, we can move on to butanol. We will take a dropper. We have our butanol sample here. We'll take a few drops of butanol and we will add it to our sodium carbonate here. Please observe if there is any reaction. Do you see effervescence, or do you see formation of any bubbles here? The answer would be no. You do not see the formation of any bubbles in this petri dish. When you add sodium carbonate and butanol together, there won't be any reaction taking place. This is because, again, butanol is not acidic enough to show a reaction with sodium carbonate. Then we have benzyl alcohol. Let's add a few drops of benzyl alcohol. Let's add a few drops of benzyl alcohol to our sodium carbonate that we have here. Again, students, when we added benzyl alcohol to sodium carbonate, we did not see the formation of bubbles. This would indicate that benzyl alcohol was also not acidic enough to react with sodium carbonate. With this, I can now disclose the fact that alcohols are not acidic enough to react with sodium carbonate. Alcohols and sodium carbonate will not show a reaction no matter what the alcohol we use. You will not see a reaction between alcohol and sodium carbonate. This is because alcohols, as I mentioned earlier, are weak acids. They are not going to be able to show any reaction with sodium carbonate. Not only that, alcohols will not show a reaction with sodium hydroxide as well. They are not acidic enough to show a reaction with sodium hydroxide, but alcohols are acidic enough to show a reaction with metallic sodium. Now, students, let's move on to one additional step where we are going to disclose how sodium carbonate will react if it is added with a carboxylic acid. So, as you know, carboxylic acids are capable of reacting with sodium carbonate. And as this reaction takes place, you can see the formation of bubbles. Now, as we did this experiment, all that I mentioned was there is no formation of bubble here, so therefore there is no reaction between sodium carbonate and the alcohol. But how would a reaction taking place between sodium carbonate and any other organic material like carboxylic acids would look like? What will the reaction between a sodium carbonate and carboxylic acid would actually look like? So, to answer that question, we have our acetic acid here and we have sodium carbonate. We will take a small amount of our sodium carbonate. So, we have our sodium carbonate. We will take a small amount of our sodium carbonate into another separate petri dish. And to this sodium carbonate, we are going to add carboxylic acid, specifically acetic acid or ethanoic acid. So now, when we add the ethanoic acid, you are going to see formation of bubbles. So we did not observe bubble formation when it comes to reacting sodium carbonate and alcohol, and you are required to know what bubble formation is going to look like when an acid reacts with the sodium carbonate that we have in front of us. So let's take our acetic acid or ethanoic acid sample here, and let's add a few drops of acetic acid onto our sodium carbonate. You can see formation of bubbles. This is the observation that confirms that sodium carbonate has reacted with an acid. Now, let's add a little bit more acetic acid to this sodium carbonate. You can very clearly see the formation of bubbles in this. This indicates that there is a reaction between sodium carbonate and acetic acid. We'll have a look at it one more time. We'll take a watch glass. We'll add a small amount of sodium carbonate to the watch glass. And let's add yet another few drops of acetic acid to the sodium carbonate. You can see the formation of bubbles very clearly here. We did not see this particular observation when it comes to reacting sodium carbonate with any of the alcohols here. This indicated that these alcohols did not show a reaction with sodium carbonate. If it had a reaction, you would have observed the formation of bubbles like we did when we reacted sodium carbonate with acetic acid. With that, students, we conclude this part of our experiment. We will now move on to the next part of our experiment. Now, in this part of our experiment, we are going to see how alcohols are going to get oxidized in the presence of an oxidizing agent such as potassium dichromate, potassium permanganate. As you know, students, you can carry out these oxidation reactions either in acidic medium or in alkaline medium. So we are going to observe how acidified potassium dichromate and acidified potassium permanganate oxidize alcohols, and then we are going to move into taking alkaline or basic potassium permanganate and react this basic medium of potassium permanganate with alcohols to observe whether alcohols are going to get oxidized in alkaline medium with potassium permanganate. So first we are going to start with acidified potassium dichromate. We have here our potassium dichromate sample, and then we are going to add sulfuric acid and acidify it, and then we will continue to do the reaction where we react alcohols with acidified potassium dichromate, which is an oxidizing agent, and we are going to observe what kind of observations can be seen when we conduct this experiment. Students, before we move on to the experiment, you have to keep in mind primary alcohols such as the alcohols we have here. We have ethanol here, we have butanol, and we have benzyl alcohol. Two of them are aliphatic alcohols, and then when it comes to benzyl alcohol, we have aromatic ring in it. So these alcohols that are primary alcohols are capable of reacting with strong oxidizing agents such as acidified potassium dichromate, and they can eventually turn into carboxylic acids. But before that, they will be turning into aldehydes. Primary alcohols first get converted into aldehydes, and then they further gets oxidized into carboxylic acids. You should not forget this. If you want to obtain the aldehyde, you can do so by reacting the alcohol and the oxidizing agent in a simple distillation setup, and you can separate it out. If you use a heat and reflux setup, you will be left with the carboxylic acid product. Anyhow, students, with that in mind, we can now move on to reacting these primary alcohols with an oxidizing agent until all of these primary alcohols get converted into carboxylic acids. And as they get converted into carboxylic acids, the oxidizing agents will undergo reduction, and due to their reduction, you will see a color change. When we use potassium dichromate, it is an orange color solution. It will turn into a green color. This is because dichromate ions are orange in color. As it undergoes oxidation, it turns into chromium 3+ ions. Chromium 3+ ions form a complex with water ligands and the sulfate ligands in the medium to form a green color. So you're going to observe the orange color of the medium changing to a green color. With this information in mind, we can now start the experiment. We will have to take a boiling tube. We will take a small volume of potassium dichromate into a boiling tube, and we will acidify this potassium dichromate. We'll take a little bit more. We will acidify this potassium dichromate by adding dilute sulfuric acid. We have here our dilute sulfuric acid. We'll add a small amount of dilute sulfuric acid to acidify this solution. Now we have prepared our acidified potassium dichromate solution. Since we have 3 alcohols here, we are going to take small portions of this potassium dichromate into 3 separate test tubes. We will take one more sample of potassium dichromate into another test tube, and we will keep this particular sample of acidified potassium dichromate for comparison. We will compare the color of this original acidified potassium dichromate sample with the other samples when they are reacted with the alcohol. As you know, students, the reaction between the oxidizing agent and the alcohol might be slow. So, to increase the rate of the reaction, we can use a water bath. We have a Bunsen burner heating up a beaker full of water, and this will act as our water bath. And once we mix the alcohol and the oxidizing agent, we can place these samples on the water bath or in the water bath and observe the reaction happening a little bit faster, and then later on we can observe the color change. Now students, it is time for us to react the acidified potassium dichromate with the 3 alcohols we have in front of us. As I mentioned earlier, we have potassium dichromate solution here. We have dilute sulfuric acid solution here. We have mixed the two together to produce a sample of acidified potassium dichromate. We have here a sample of acidified potassium dichromate. So we have added dilute sulfuric acid to potassium dichromate to produce this acidified potassium dichromate. Now we will take small portions of acidified potassium dichromate into 3 test tubes. And as you can see, these test tubes are going to be labeled A, B, and C, so that we can identify it. When we include these test tubes in the water bath, we can separately identify them because we have labeled them A, B, and C. And to a separate test tube, we will take a small portion of acidified potassium dichromate for comparison. We will keep this test tube as a control without adding anything to it. We will compare the color of the acidified potassium dichromate of this test tube with all the other test tube as the reaction proceeds. So now students, to test tube A, I'm going to take ethanol. To test tube B, I'm going to take 1 butanol. And to test tube C, I'm going to take benzyl alcohol. So ethanol and butanol are aliphatic alcohols, and benzyl alcohol is going to be an aromatic alcohol. We will take ethanol. We will add a few drops of ethanol to our test tube A. As you can see, as soon as we add ethanol into our test tube containing acidified potassium dichromate, there is no drastic change observed. However, slowly the color of acidified potassium dichromate solution is starting to turn into a green color. But at room temperature, this reaction is happening very slowly. So let's place this in a water bath and see the actual color change that takes place when the dichromate ions turn into chromium 3+ ions. As the dichromate ions turn into chromium 3+, the alcohol, which is ethanol that we used in test tube A, converts into aldehyde, which is ethanaldehyde, and then the ethanaldehyde gets further oxidized into ethanoic acid. So as the alcohol oxidizes, the dichromate ions here gets reduced to forming chromium 3+ ions. As I mentioned earlier, chromium 3+ ions will form coordinate bonds with water ligands and the sulfate ions that are present in this medium, because we have acidified this medium with sulfuric acid. Due to this, the complex that is formed is going to be green in color. As you can see, students, the solution has not mixed well, but the top part of this solution is starting to turn green. And since we haven't mixed it really well, still the bottom part of this solution is orange in color. Now compared to only acidified potassium dichromate, you can see the color change. We'll leave it a little while in the water bath. We'll mix it first. We'll mix it really well first. I think now you can see the green color a bit more clearly. But we'll place it in the water bath for another few seconds. We can very clearly see the solution has turned to a green color. So we had our ethanol reacting with acidified potassium dichromate, and now the dichromate solution has changed its color from orange to a green color that you observe here. We can now move on to butanol. So into this test tube labeled B, we are going to add a small amount of butanol. We have our butanol here. We'll add only a few drops of butanol into this mixture. As you can see, when butanol is added to this acidified potassium dichromate solution, they are forming two layers. As butanol doesn't dissolve in water, and this is an aqueous solution, you can see the acidified potassium dichromate layer and butanol layer separately. We will mix them a little bit as much as we can and to observe whether acidified potassium dichromate is capable of oxidizing butanol. Now, after mixing it really well, let's place this in a water bath to increase the rate of the reaction and observe this orange color that we observe in this solution changing into a green color. Now, students, you are going to observe that this solution is no longer orange. We started with this orange color that I have on my left hand. So the test tube on the left hand has just acidified potassium dichromate, but you can see now very clearly, you can see the test tube on the right hand side has a solution that is green in color. This is because the chromium 3 plus ions have been formed and the butanol alcohol has actually converted into butanoic acid. Now, let's move on to our aromatic alcohol, which is benzyl alcohol. Aromatic benzyl alcohol here. We'll take a few drops of our benzyl alcohol into our test tube that we have here. And as you see, benzyl alcohol does not mix well with an aqueous solution, so therefore there is layer separation. Although it has started to react with acidified dichromate, it is not a drastic reaction that takes place at a faster rate. So to increase its rate, we are going to mix it really well and then add this to our water bath. As you can see, it doesn't mix really well with an aqueous medium. However, we are going to, after mixing it thoroughly, we are going to add it into our water bath and we are going to wait till it reacts with acidified potassium dichromate and changes its color from orange to green. And as this happens, the benzyl alcohol gets converted into benzoic acid. Benzyl alcohol converts into benzoic acid. So this is an oxidation reaction. And benzoic acid is not soluble in water. So therefore, you will be able to see benzoic acid precipitating out as a white color precipitate. Now students, we are starting to see the formation of a white color precipitate. If you observe over here, you can see white color particles or crystalline particles are appearing in this solution, and the solution is no longer orange, it is green. So this indicates even our benzyl alcohol got oxidized to form benzoic acid. And when I shake it, you can see tiny white particles swirling around. These white particles are benzoic acid crystals. As benzoic acid is insoluble in water, it is going to form white color benzoic acid crystals and separate out from the aqueous medium. So students, we observed how alcohols react with acidified potassium dichromate. We observed how alcohols react with acidified potassium dichromate. As alcohols react with acidified potassium dichromate, we observed all of the alcohols got converted into their carboxylic acid, and while getting oxidized, the dichromate ion got reduced to forming chromium 3 plus ions. While the alcohols got oxidized into forming their respective carboxylic acid, the dichromate ion got reduced to form chromium 3 plus ions, and chromium 3 plus ions in an aqueous medium that contains sulfate ions forms a complex that is a green in color. So chromium 3 plus ions often appear as a green color complex because they form coordinate bonds with water ligands other than water ligands, sulfate ligands and chloride ligands in the medium. They will also connect to those ligands, forming complexes that are green in color. A hexa aqua chromium 3 complex is going to be violet in color. However, since we have sulfate ions in the medium, it is not going to form a hexa aqua chromium 3 plus or chromium 3 complex. It will form coordinate bonds with water ligands along with sulfate ligands, forming green color complexes that you observed a little while ago. Now, let's move on to the second part of this experiment with oxidizing agents. We will now use acidified potassium permanganate and observe how alcohols get oxidized in the presence of acidified potassium permanganate. Now, in this part of our experiment, we are going to see how alcohols react with acidified potassium permanganate. As you may know, acidified potassium permanganate is a very good oxidizing agent, and we actually see it being used for many reactions when you are studying organic chemistry. So, we have here our potassium permanganate solution. We can take a small amount of our potassium permanganate solution into a boiling tube. As you can see, the potassium permanganate solution is purple in color. This is because the permanganate ions are purple in color. Now to this, we can add a small amount of dilute sulfuric acid. Now we have added a small amount of dilute sulfuric acid and made this potassium permanganate solution acidic. So now we have prepared an acidified potassium permanganate solution. To ensure that it mixed really well, we will transfer it to another boiling tube back and forth like this, so that we can ensure that it has mixed really well. Now, like we did in the previous experiment, we will take small portions of this acidified potassium permanganate solution into 3 different test tubes. So these test tubes are labeled A, B and C, and then to an unlabeled test tube we will take a small amount of acidified potassium permanganate for comparison purposes. And now everyone, we have taken equal portions of acidified potassium permanganate into each of these test tubes, and now we are going to add the alcohol to each of these test tubes. Keep in mind, when alcohol is reacting with acidified potassium permanganate, it gets reduced. The acidified potassium permanganate gets reduced to Mn2 plus. So the MnO4 minus ion or the permanganate ion is the reason that you observe this purple color in this acidified potassium permanganate solution. This purple color is due to MnO4 minus ion or permanganate ion. When the permanganate ion gets reduced, when the alcohol gets oxidized to the aldehyde and then the aldehyde gets oxidized to the carboxylic acid, when this reaction is happening, the permanganate ion gets reduced to Mn2 plus. So to repeat what I just said, when we are adding a primary alcohol to acidified potassium permanganate, the primary alcohol first gets oxidized to form an aldehyde, and then it further oxidizes to form a carboxylic acid. As I mentioned earlier, if you take a secondary alcohol, it will get oxidized to a ketone. Tertiary alcohols will not show a reaction with oxidizing agents such as acidified potassium permanganate. So as the alcohol gets oxidized, the potassium permanganate or the permanganate ions in the solution gets reduced to Mn2+. And as you know, the color of Mn2+ aqueous ion solutions are referred to as a pale pink color. But in a lab environment, observing this pale pink color of Mn2+ ions is quite difficult, as this pale pink color is very low in its color intensity, and only at really high concentrations of Mn2+ we can observe this pale pink color. So majority of the time when permanganate ions gets reduced to Mn2+, the color change would be from purple to colorless. So permanganate ions are considered to be purple in color, and Mn2+ aqueous ion solutions are going to appear colorless. So when it comes to our alcohols reacting with this acidified potassium permanganate as well, we are going to observe these color changes. This purple color solution should turn colorless. Now to test tube A, let's add our ethanol solution. We have our ethanol solution here. We'll take a clean dropper and we will add a few drops of ethanol to our acidified potassium permanganate solution. As you can see, students, when you introduce acidified potassium permanganate and alcohol together, or when you add alcohol into a solution of acidified potassium permanganate, you won't see a very drastic color change instantly. However, little by little, the color of acidified potassium permanganate will start to change. Now, on my left hand, I have the original acidified potassium permanganate solution, and on my right hand, I have the acidified potassium permanganate solution that is added with ethanol. You can very clearly see slowly the color of potassium permanganate is starting to change. It is turning colorless. Now this reaction is happening fairly slowly. So if you mix it really well and then place it in a water bath, you will see that this solution will turn completely colorless. Now we have placed it in a water bath. We will wait for a while for it to turn colorless. Now students, within a matter of few seconds or close to a minute, we can now observe that the acidified potassium permanganate had a purple color initially, but when it was reacted with ethanol and heated with the use of a water bath, we can see the color of permanganate ions have completely disappeared. So again, for comparison, we will bring acidified potassium permanganate solution right next to this colorless solution. You can observe how the purple color has changed. This indicates that acidified potassium permanganate is capable of oxidizing ethanol. Now we will move on to butanol. We have our butanol here. We'll take another clean dropper and we'll take a small amount of butanol and add it to our test tube B, which again contains acidified potassium permanganate. Now students, you can very clearly see, since butanol is not very soluble in water, there is a layer separation here. Now at the bottom of this test tube you find acidified potassium permanganate aqueous solution. Solution is aqueous, which means that this acidified potassium permanganate was dissolved in water. But when it comes to butanol, it is not soluble in water. We observed that in the initial parts of this experiment. So you can see a small layer of butanol or 1-butanol is found on the top of this particular reaction mixture. We can try to mix it, and as the butanol reacts with the acidified potassium permanganate, it will get used up. So you can see later on when the reaction is done, the amount of butanol found on the top layer will be less. So even now you can observe the reaction is taking place very slowly. Even now you can observe the reaction is taking place very slowly because the color of the acidified potassium permanganate solution is decreasing. So to speed up this reaction, let's place it in a water bath. Before doing so, we can mix this reaction mixture really well, and then we will place it in a water bath to observe the color change. Students, we can see the color is changing from purple to colorless. So please observe how the color is changing inside this test tube that we have placed on the water bath. Now students, we have kept this test tube B in the water bath for about a minute. Now let's take it out. As you take it out, you can observe that this test tube now appears colorless. Earlier on, the potassium permanganate solution was purple in color, but now it has turned completely colorless. And you do not see two layers here. You do not observe two layers being present here. One of the reasons why you don't observe two layers is that I added only a small amount of butanol. And as butanol reacts with potassium permanganate, it converts into butanoic acid. Butanoic acid is more soluble than butanol in water. So when it comes to butanoic acid that is produced here, it dissolves in water to form a single layer. However, to demonstrate, if I have added more butanol, that additional amount of butanol would be present as a layer above our clear solution. As you can see, if I had added excess amount of butanol, then the unreacted amount of butanol would be present as a separate layer on top of our solution. So at the bottom we have the aqueous solution, and on the top we have the unreacted amount of butanol. Now Let's go through the reaction that happened when it comes to reacting butane 1-ol or 1-butanol with potassium permanganate. As butane 1-ol or 1-butanol reacts with potassium permanganate, the alcohol will get oxidized to form the carboxylic acid, which is butanoic acid. And as you know, butane 1-ol and water does not mix really well. Their solubility is quite low. So when you add butane 1-ol and water together, there will be two layers. But as butanol reacts with acidified potassium permanganate, it will get used up and will form butanoic acid, which is more soluble in water than butanol. So therefore, the product that is formed here is dissolved in water. Therefore, you would not see a layer separation. So the only reason why you see a layer separation here is because I have added an additional amount of butanol after we took the test tube out of the water bath to indicate if there was excess amount of butanol that they would form a layer. To indicate that they would form a layer, if excess amount of butanol was added, I have included a additional layer of butanol over here. Now let's move on to addition of benzyl alcohol to our acidified potassium permanganate solution here. We'll take a clean dropper and we'll add only a few drops of benzyl alcohol. We'll add about 4 to 5 drops of benzyl alcohol. So as you can see, upon addition of benzyl alcohol to potassium permanganate, the color of potassium permanganate has started to change. It was purple in color, but now you can see it is gradually turning colorless. And as you may recall, benzyl alcohol is not soluble in water. Benzyl alcohol is not very soluble in water, but as it reacts with acidified potassium permanganate, it will form a carboxylic acid, which is benzoic acid. And benzoic acid is not going to be very soluble in water either. It is going to precipitate out as a white color precipitate. So to observe this a bit more clearly, we will place this in a water bath. Before we place it in a water bath, we will mix it really well. As you can see, as soon as I mix it, we can see the color of potassium permanganate disappear. To observe this a bit more clearly, we will take a little bit of acidified potassium permanganate and add even a bit more. And you can see now, when acidified potassium permanganate was reacted with benzyl alcohol, it got oxidized to form benzoic acid. And if you observe here very clearly, the benzoic acid that is formed is not very soluble in water. Benzoic acid is insoluble in water. So therefore, it will precipitate out as a white color crystalline solid. Even right now, you can see a white color crystalline solid is dispersed in this aqueous medium. Around this area, you can see a white color crystalline solid dispersed in this aqueous medium because, as you may know, benzoic acid that is formed here due to oxidation of benzyl alcohol is not soluble in water. We did not have to heat this reaction up because this reaction was somewhat faster compared to the other two reactions. In this part of our experiment, we saw how acidified potassium permanganate would react with different alcohols. We reacted acidified potassium permanganate with ethanol, butanol, and benzyl alcohol. Ethanol, butanol, and benzyl alcohol. And in each of these cases, we observed that acidified potassium permanganate loses its color as the reaction takes place, as permanganate ions convert into Mn2+, we see a color change of purple to colorless. Permanganate ions were purple in color, Mn2 plus ions are colorless. So as the alcohols get oxidized to form their respective carboxylic acids, the MnO4 minus ions get converted to Mn2 plus, which will appear colorless. When ethanol was reacted with potassium permanganate, it formed ethanoic acid. When butanol was reacted with potassium permanganate, it formed butanoic acid. Butanol produced butanoic acid. And when benzyl alcohol was reacted with acidified potassium permanganate, it formed benzoic acid, which was also insoluble in water, which led to the precipitating out of benzoic acid in the aqueous medium. And while these reactions were happening, the purple color of the acidified potassium permanganate solution turned to a colorless solution. Purple color turned to colorless. Now, with this information, we can move on to the next experiment where we will react each of these alcohols with potassium permanganate in alkaline medium. In this part of our experiment, we are going to be observing how each of these alcohols, primary alcohols, how each of these primary alcohols will react with potassium permanganate in an alkaline medium. So we are going to take our potassium permanganate solution that we have in front of us, and then we are going to add sodium carbonate to make it alkaline. So to make our potassium permanganate solution alkaline, we are going to add sodium carbonate. After making the potassium permanganate solution alkaline, we are going to add ethanol, butanol, and benzyl alcohol to each of these test tubes along with our alkaline potassium permanganate solutions. And we are going to heat these reaction mixtures with the help of our water bath, and we are going to observe the color change. Now keep in mind, students, unlike in acidic medium, potassium permanganate does not get reduced to Mn2 plus. When it comes to alkaline medium, potassium permanganate gets reduced to MnO2, manganese dioxide, which is a water-insoluble brown color solid. So because of this, the observation when we are oxidizing an alcohol with the use of alkaline potassium permanganate is not going to be the same as when we conducted this experiment with the use of acidified potassium permanganate. When it comes to the acidified potassium permanganate related experiment that we conducted in the previous section, we saw the color of the potassium permanganate solution changed from purple to colorless. But when it comes to the alkaline medium, it is going to be from purple to forming a brown color precipitate. But keep in mind, students, this brown color MnO2 solid that is formed as really fine particles, really fine solid particles, and these really fine solid particles will get dispersed in the aqueous medium, giving it more of a look of a solution. But you have to understand what we form here is not a solution of MnO2, but what we form here is basically a suspension of MnO2 or manganese dioxide. So keeping that in mind, we will move on to making this aqueous potassium permanganate solution alkaline. In order to do that, we have to first take a small amount of potassium permanganate into a boiling tube, or we can take a boiling tube and add a small amount of sodium carbonate, and to that we can add potassium permanganate solution and create an alkaline or basic potassium permanganate solution. Now we'll take a boiling tube and we can add a small amount of sodium carbonate. We can take a small amount of sodium carbonate into this test tube, into this boiling tube, and we can add potassium permanganate solution to this boiling tube now. So we have our aqueous potassium permanganate solution here. We will add potassium permanganate to the sodium carbonate that we have taken into our boiling tube. And to mix it thoroughly, we will take another boiling tube and transfer this back and forth. Now students, we have formed a potassium permanganate solution in alkaline medium. Like we did in the previous experiment, we'll take small portions of this alkaline potassium permanganate solution into 3 test tubes. And for comparison, we'll take another test tube and we will add a small portion of our alkaline potassium permanganate solution, and we'll keep it on our test tube rack. So students, to the test tube labeled A, we are going to add a small amount of ethanol, and we are going to observe if an oxidation reaction takes place when we add ethanol to this alkaline potassium permanganate solution. We have our ethanol here. We will take a small portion, or we will take a few drops of ethanol, and we will add it to our alkaline potassium permanganate solution. Now students, you might notice this reaction is not going to be happening really fast, so we will have to heat it with the use of a water bath. I'm going to place this test tube in a water bath and observe if the reaction happens faster in a water bath. The color of this solution starts to change. Now, original alkaline potassium permanganate solution was purple in color, but now you can see it has started to change. And if you observe closely, you can notice that it is turning into a brown color. It is turning into a brown color, and small particles of manganese dioxide are actually getting formed here. So therefore, the solution is turning brown in color. But keep in mind, as I mentioned earlier, this is not a brown color solution that you have formed. This brown color that you observe in this aqueous medium is not due to the formation of a brown color solution. Instead, this brown coloration is observed due to formation of MnO2, manganese dioxide, which is a water-insoluble solid. However, MnO2 is produced here as really fine solid particles, and these solid particles are dispersed in this aqueous medium evenly, creating the illusion of it being a solution. But keep in mind, students, this is not a solution. This is not that clear as well. If you pay close attention to it, it is not very clear. It is translucent due to the fact that you have solid particles dispersed here, creating a suspension of MnO2 solid. So this observation confirms that alcohols such as ethanol can get oxidized in alkaline potassium permanganate solutions. So what are the products that are formed here? Permanganate ions got converted into MnO2. Permanganate ions are purple in color. MnO2 is a brown color solid, which is insoluble in water. And what happened to the ethanol? Ethanol got converted into ethanoic acid, but keep in mind, students, this ethanoic acid is formed in alkaline medium. So the acid will react with the basic alkaline medium that we have here and will be forming a carboxylate anion. So what you have here as the alcohol oxidizes is the ethanoate ion. So the carboxylate ions get formed when you carry out an oxidation reaction with the help of alkaline potassium permanganate. In alkaline medium, you do not form the respective carboxylic acid. Instead, you will form the carboxylate anion. So over here, what you are observing is MnO2, manganese dioxide, and the ethanol actually converted into sodium ethanoate. Sodium ethanoate is present here. Now let's move on to the next alcohol. Now we will take our butanol and we will again take a clean dropper. We will take a small sample of butanol and we will add a few drops of butanol. We'll add a few drops of butanol to our alkaline potassium permanganate solution. And you might have noticed I took caution not to add too much butanol. This is because if you have certain amount of unreacted butanol, then you will observe this unreacted butanol as a separate layer after the color change has happened. So to avoid having that observation, we can add a few drops of butanol as our practical textbook suggests. And when the reaction proceeds, you will see this butanol that is separated out here as a layer on top of the alkaline potassium permanganate solution will get used up, and you will not have two layers formed here in this reaction mixture. After the reaction has gone to completion, you will not observe two layers if all of the butanol that I have added has reacted. Now, students, before I place it in the water bath, I will mix it well, and then I will place it in our water bath. So, as we wait, please note how the color of this reaction mixture changes as we heat the reaction mixture. Now, students, you can see the color has started to change. It has not completely changed yet, but you can see since the solution is still quite warm, after I took it out of the water bath, the reaction continued to take place, and now we can see the correct color. You can see the color of this mixture is now brown. So again, like in the previous instance, we have formed a brown color suspension of manganese dioxide, MnO2. The permanganate ions have turned into MnO2 solid, and this fine particles of solids that are formed here is dispersed throughout the aqueous medium, producing this brown color suspension we have over here. Now students, you might have observed that there is no two layers present in this reaction mixture. As I mentioned earlier, when I added butanol into the reaction mixture initially, I took precaution to add only a small amount of butanol. So the total amount of butanol that I have added into this reaction mixture has reacted with the alkaline potassium permanganate solution. If there was an excess amount of butanol present in the reaction mixture, you would observe that as a separate layer on top of this aqueous layer. So the only reason that you don't observe this butanol layer or separate butanol layer is because I have not added excess butanol to the reaction mixture. And the product that is formed here when potassium permanganate in an alkaline medium reacts with butanol is butanoate anion. We form a carboxylate anion which is butanoate, and since sodium ions are present in the aqueous medium here, we can say we have produced sodium butanoate. Now let's move on to the next alcohol that we have here with us. So now we will take our benzyl alcohol. We will take a dropper and we will add a very small amount of benzyl alcohol to our alkaline potassium permanganate solution. As you can see, the benzyl alcohol and the alkaline potassium permanganate solution do not mix really well, but it has a bit of a faster reaction rate compared to the other two alcohols with alkaline potassium permanganate. You can see before even heating it, there is a slight color change that we can observe here. We will place this, after mixing it really well, we will place it in the water bath. But students, we didn't have to place it in the water bath. Even before placing it in the water bath, we saw a brown color suspension has been formed here, but we will keep it in the water bath for a while and then get back to it to see if it produces a clearer color change. Now we can see over here as well, we have formed a brown color suspension of MnO2, manganese dioxide. Again, I mentioned it's a water insoluble brown color solid, and what you have here is a suspension of that. Now students, one thing that you have to understand is when benzyl alcohol got reacted with acidified potassium permanganate, you saw, apart from the color change of the permanganate ion, we saw the formation of a white color crystalline solid. What was that white color crystalline solid when benzyl alcohol reacted with acidified potassium permanganate? That was benzoic acid. Benzoic acid was formed. However, in alkaline medium, what you form is benzoate anion. We form sodium benzoate here. Because sodium ions are in the aqueous medium, we can say that we have formed sodium benzoate. And sodium benzoate is soluble in water. So you would not observe formation of white color benzoic acid crystals. But in acidic potassium permanganate medium, when you conduct this oxidation reaction using benzyl alcohol, you will observe the formation of benzoic acid crystals which are white color solid crystals. And when you conduct the same oxidation reaction with the use of an alkaline medium, you are going to observe the formation of sodium benzoate, which is soluble in water, so you will not observe the formation of a white color precipitate here. Only the brown color precipitate, manganese dioxide, will be observed here, but since it is going to be produced as such fine particles dispersed in aqueous medium, you are going to observe a brown color suspension like this one over here. You are going to observe a suspension of brown color solid particles, which are basically MnO2 solid particles. Now students, let's move on to the next part of our experiment. In this final part of our experiment, we are going to observe how alcohols react with carboxylic acids. As you know, alcohols and carboxylic acids can react with one another to produce esters. To produce esters, you would require the presence of a catalyst such as concentrated sulfuric acid. So if you react an alcohol and carboxylic acid in the presence of concentrated sulfuric acid, you will be producing an ester. Esters are volatile, fragrant compounds. So as you produce these esters, you are going to observe or note the pleasant smells accompanied by these esters. We actually can use these smells to identify the type of ester that is actually formed. So today we are going to react ethanol, butanol and benzyl alcohol with acetic acid or ethanoic acid. Acetic acid, IUP is the name of acetic acid, is ethanoic acid. We'll be using acetic acid and salicylic acid to react with these three alcohols that I just mentioned earlier, and we are going to produce esters. And we are going to observe the different smells accompanied by the esters formed when we carry out this reaction. Unfortunately, you will not be able to note the smells released by these esters that I will be forming today, but I can communicate to you what these esters smell like. So let's first take our ethanol. We have to take 1 cubic centimeters of ethanol and we have to mix it with 1 cubic centimeter of acetic acid, and we have to add a few drops of concentrated sulfuric acid. We have our concentrated sulfuric acid. So we are going to add a few drops of concentrated sulfuric acid, and then we are going to heat this mixture. And upon heating for a while, you are going to observe that an ester has been formed with the very characteristic smell the test tube will start releasing. Now, let's move on and conduct this experiment. Now students, we have set up our water bath here. All that we have to do is take 1 cubic centimeter of ethanol, 1 cubic centimeter of acetic acid, and mix it in this test tube labeled A. And after mixing the two, we will be adding the catalyst, which is concentrated sulfuric acid. We will add a few drops of concentrated sulfuric acid, and then we will be heating the reaction mixture to obtain our ester. Let's take a clean dropper and add about 1 cubic centimeter of ethanol. And now students, we have taken 1 cubic centimeter of ethanol into our test tube. Now we can move on to adding 1 cubic centimeter of acetic acid. Now we have added acetic acid and ethanol. You can see these two compounds mix well in one another, and then we'll be adding a few drops of concentrated sulfuric acid. We have our concentrated sulfuric acid here. We can take it over here so that it will be easier for us to use it. And we will add just a few drops of concentrated sulfuric acid. Keep in mind, students, concentrated sulfuric acid, when you're handling it, you have to be very careful. You do not want to get concentrated sulfuric acid on your hands. So now we have added the catalyst concentrated sulfuric acid into the reaction mixture, and now we can place this test tube in a water bath for the reaction to take place at a higher temperature. Now students, we have allowed this reaction to take place in this water bath for a while, and we have prepared our ester, and this prepared ester is going to be added to a ice water bath, or we are going to add this ester to cold water. So we have a small amount of cold water here. We have some ice. We can add a small amount of ice to this water and make it even more cold. And now students, we will be adding this ester that we have formed into our water that we have over here. Students, this particular ester that is formed has a very sweet smelling fragrance. Usually, majority of the esters that we form have a very pleasant odor. This ester is no different. It has a very pleasant, sweet odor, similar to the odor of pear drops. Now, we will explain why we added the ester that is formed onto ice water or cold water. As you know, we prepare the ester by mixing a carboxylic acid and an alcohol with the use of concentrated sulfuric acid as a catalyst. So as you add this reaction mixture into cold water, one of the things that we plan on achieving is dissolving the excess amount of alcohol and the carboxylic acid present in the medium in this water. However, the ester that is formed is not very soluble in water. Compared to the alcohol and the carboxylic acid that we use, esters are going to be slightly less soluble than those two organic compounds that I just mentioned. So therefore, esters will mostly be on the surface of this water, and the two organic compounds, carboxylic acids and alcohols, will mostly be tucked away in the solution. However, this will change if you introduce carboxylic acids and alcohols that have a long carbon chain. But in this particular experiment, we are using acetic acid and ethanol. These are fairly soluble in water, but the ester that is formed is not going to be as soluble as ethanoic acid and ethanol. So therefore, we can very easily observe the smell or note the smell, as the ester is going to linger on the surface of this water layer. And esters are quite volatile, so therefore they will evaporate easily and you can observe the smell. Apart from that, students, one of the other concerns we have is we might have excess concentrated sulfuric acid in the mixture. So if you add it to room temperature water or water at room temperature, when the concentrated sulfuric acid gets diluted, since it is an exothermic reaction, a lot of energy will be released. This will cause the hydrolysis of the ester, or this can cause the hydrolysis of the ester. As you know, at higher temperatures in the presence of sulfuric acid, you can cause the ester to undergo hydrolysis to produce the carboxylic acid and the alcohol again. So to prevent this from happening, you can introduce the ester to cold water. Now, students, we have observed the formation of one ester when we reacted ethyl alcohol with acetic acid. Ethyl alcohol with acetic acid, you form ethyl acetate ester. We will call it ethyl ethanoate. The IUPAC name would be ethyl ethanoate. However, ethyl acetate ester that we have formed, we observed the characteristic smell of ethyl acetate, and then we went on to explain why we add the ethyl acetate to cold water. Now, we will be moving on to our second experiment. In this experiment, we are going to take butanol and react it with acetic acid. So, into our second test tube, we will take butanol. Into our second test tube, we will take butanol. We have our 1 butanol here, and we will take a small amount of butanol. We'll take a small amount of butanol, and after that we will add a small amount of acetic acid. We have our acetic acid here. We are going to add a small amount of acetic acid. After mixing these two organic compounds, the carboxylic acid and the alcohol, we are going to add a small amount of concentrated sulfuric acid. Let's add a few drops of concentrated sulfuric acid. After adding concentrated sulfuric acid as a catalyst, we are going to place this test tube in a water bath for the esterification reaction to take place. Now, while the reaction takes place, we can remind ourselves the kind of reaction that takes place here. When a carboxylic acid and an alcohol reacts with one another, it forms an ester. This is a condensation reaction. When two molecules are added together while forming one large molecule and a small molecule such as H2O or HCl, we have conducted a condensation reaction. So a condensation reaction is a reaction where when two molecules are added to form one large molecule while releasing a small molecule like water or HCl, that is known as a condensation reaction. So an ester can be formed by a carboxylic acid reacting with an alcohol or an acyl chloride reacting with an alcohol. Now students, I'm getting the smell of the ester. When the reaction is completed, usually you get a very pleasant smell of the ester. So before we add this to our water we have here, we have a new volume of water which is not added with anything else, and we are going to add a little bit of ice. We have already made it cool by keeping it refrigerated. However, we are adding a little bit of additional ice to make sure that the water remains cool. And then we are going to take this ester that we have formed here, and we are going to add a portion of it onto our cold water that we have here. Students, the ester that we have formed here is butyl acetate or butyl ethanoate. Butyl acetate or butyl ethanoate. So this butyl ethanoate or butyl acetate ester has a very characteristic smell, which is the smell of apples. It's a very fruity, very pleasant apple smell that you will feel when you conduct this experiment. You will get the smell of apples from butyl ethanoate or butyl acetate. Now, let's move on to the third ester we will be producing here in this lab. In this part of our experiment, we are going to use benzyl alcohol. We are going to take 1 cubic centimeter of benzyl alcohol, or we can say we are going to take a small portion of benzyl alcohol. And to this benzyl alcohol, we are going to add acetic acid. So we will take again a similar volume of acetic acid. We'll take a similar volume of acetic acid and we will add it to our test tube C. We can see, although benzyl alcohol was not soluble in water, in acetic acid it is soluble. Since both of them are organic solvents, they are capable of dissolving one another. And after mixing these two organic compounds, we are going to add a little bit of the catalyst, which is concentrated sulfuric acid. We have here our concentrated sulfuric acid. We will be adding a few drops of concentrated sulfuric acid into our reaction mixture. After adding the two, we will heat the reaction mixture to observe the characteristic smell of the ester that is formed in this reaction. While we heat this reaction mixture, we can take a water sample here and we can add a small amount of ice. We can add a small amount of ice to cool the water that we have over here. And after the ester has formed, we can transfer a small amount of the ester into this cold water and observe the smell that is released by this ester. Now students, we have allowed this test tube to stay in the water bath for a while. So the ester has formed here Now, let's pour this ester to the cold water we have here and observe the smell. You observe a very nice floral smell here. It is somewhat characteristic of the smell of jasmine. So, what you observe here is a floral smell that is characteristic of the smell of jasmine. So, we have formed here by mixing benzyl alcohol and acetic acid here, and we formed benzyl acetate, which has a characteristic floral smell, actually very similar to the smell of jasmine. So, students, we have made three esters. First ester we made was ethyl acetate by mixing ethanol and acetic acid, and then we produced butyl acetate, which had the smell of apples. It was formed by mixing butanol and acetic acid, and finally we mix benzyl alcohol with acetic acid to form benzyl acetate, and that had a characteristic smell of jasmine. And when it comes to our ethyl acetate, it had a very pleasant fruity smell, characteristic of the pear fruit. So now let's move on to the next part of this experiment, where we will be using all of these alcohols along with salicylic acid to produce different esters. Now, students, we are going to react salicylic acid with ethanol, butanol, and benzyl alcohol. To this test tube labeled A, we'll take a small amount of ethanol. We have here our ethanol. We'll take a small amount of ethanol into this test tube. Now you can see we have taken a small volume of ethanol. To this, we are going to add a small amount of salicylic acid. So let's take a small portion of salicylic acid and let's add a very small amount of salicylic acid into our test tube here. As you can see, we can dissolve the salicylic acid in ethanol. All of the white color solid we saw earlier is now dissolved in ethanol. After that, we can move on to adding a few drops of sulfuric acid. Now we have added a few drops of sulfuric acid as a catalyst, and now we can place it in our water bath. So as this reaction takes place, we can bring out a little bit of cold water to make sure that it stays cold. We can add a small amount of ice as well. After we have allowed this reaction to take place in this test tube for a while, we can then transfer the ester that is formed into this cold water that we have with us. Now, students, we can observe, now I'm starting to feel the characteristic smell that is emitted by the ester that is released here. We have reacted salicylic acid with ethanol and formed ethyl salicylate ester, and even without pouring it onto water, we can feel the strong characteristic smell that is emitted by ethyl salicylate. Now let's pour it over some cold water. Students, it gives off a very pleasant, sweet wintergreen smell. If you had formed methyl salicylate will give a very strong wintergreen smell, and ethyl salicylate is going to give a bit of a faint, sweet wintergreen smell. So students, when we conducted this experiment, we observed that ethyl salicylate ester was formed, and it had a characteristic smell that we could use to identify the presence of ethyl salicylate. Now let's move on to the next reaction, where we will be reacting butanol with salicylic acid. Now we are going to take butanol and we are going to take about 1 to 2 cubic centimeters of butanol into a test tube. And to this, we will add salicylic acid. We have our salicylic acid here, and we'll take a small amount of salicylic acid and we will add it to our butanol that we have here in this test tube. As you can see, when you mix this, the salicylic acid will dissolve in butanol. And now we will move on to adding a small amount of our catalyst, which is sulfuric acid. We added a few drops of sulfuric acid here. We can proceed to add a few more drops. After adding a few drops of sulfuric acid, we can place this reaction mixture in a water bath to heat it up. While we wait for this reaction mixture to produce an ester, we'll take a small volume of water here and we will add a little bit of ice. To make it cold. And we will wait for this reaction to go to completion. Students, we have formed the ester here. So we mixed two organic compounds. We mixed salicylic acid with butan 1-ol or 1-butanol. And what you have formed here is a butyl salicylate ester. And right now I can feel the characteristic smell of butyl salicylate. So now let's take this butyl salicylate ester and pour it over our cold water. And now let's observe the smell. Students, the smell of butyl salicylate is characterized as a rough, herbaceous, medicinal smell. A rough, herbaceous, medicinal smell is a smell that you will be experiencing when producing butyl salicylate ester. Now we will move on to the preparation of our final ester with the use of benzyl alcohol and salicylic acid. Students, we have our benzyl alcohol here. Let's take small volume of benzyl alcohol into the test tube C. And then we'll take salicylic acid. We'll take a small amount of salicylic acid. We'll take a small amount of salicylic acid and we will add it to our benzyl alcohol. We have added salicylic acid to our benzyl alcohol that we have here. Now let's add a few drops of concentrated sulfuric acid. And after mixing the mixture, let's place it on a water bath. Now we will take small amount of water into a beaker. We will add a little bit of ice to cool this water. And after the ester has been formed, we will pour the ester onto our cool water. Now students, we have produced our ester here. We used benzyl alcohol and salicylic acid to produce this, and the ester that is formed here is known as benzyl salicylate. We have produced benzyl salicylate and it also has a very characteristic smell. Let's pour this onto our cold water. Students, what you observe here is a very faint smell compared to the other esters that we made in the lab today. This ester has a very faint smell, and this ester has a bit of a floral smell. So the characteristic smell of benzyl salicylate would be a faint floral smell. So students, to sum it up, we added ethanol with salicylic acid to form ethyl salicylate. Then we reacted butanol with salicylic acid to form butyl salicylate. Finally, we reacted benzyl alcohol with salicylic acid to produce benzyl salicylate. So students, after conducting this part of our experiment, we realized when we react different alcohols with different carboxylic acids, we are capable of producing different esters. We reacted these three alcohols with acetic acid and with salicylic acid to produce a variety of different esters, and we realized each of these esters had their own characteristic smell. Some of these esters had a very clear characteristic smell which could be used to identify the presence of that particular ester in a reaction mixture. So we have now come to learn that different esters have different smells. Majority of the esters have a very pleasant smell. So you find these ester compounds in majority of the products that you come across on a day-to-day basis. With that, students, we conclude today's experiment, and let's move on to some questions and other important theory parts revolving around this experiment. Students, now we are back in the classroom. After having a look at how we conduct the experiment, it is now time for us to take a look at some questions that are revolving around experiment number 25. So let's take a look at the first question. Using CH3CH2CH2OH, which is butane-1-ol, as the only organic compound provided to you, show how you may synthesize the below compound. Now the below compound is a glycol, or also referred to as a diol. So as soon as you see a diol or a glycol, you should remember how we used an alkene to produce a diol. So alkenes can be turned into diols when we react alkenes with alkaline medium potassium permanganate. So that means we would have had a double bond between these two carbons in the previous step before we got this final product. And we would have had, we can add alkaline medium potassium permanganate to convert it into a diol like this. So now we have to focus on obtaining a double bond here. So when we are given with this particular substance first, since we know now we have to obtain a double bond here, we can start and we can work our way towards obtaining a double bond between the second and the third carbon. So we can do it like this, students. So we have been given CH3, CH2, CH2, CH2OH. Now if you react this with anhydrous aluminium oxide, Al2O3, and if you heat it, then you will obtain a double bond, but not necessarily in the position we want. However, we will obtain a double bond. We have a double bond formed here, and the rest will undergo no change. So the double bond is here, but we want it to be here. We want it to be here. So then we can add HBr. So if you add HBr, now the reason for us to add HBr is we need the double bond to be shifted here. So we have to somehow get to another method of forming a double bond. So we can't work with having this double bond here. We have to again somehow shift this double bond over here. We can add HBr and see if that will help us. So if you add HBr at that point in polar medium, now this will follow the Markovnikov's rule. So hydrogen will be attached to the place where there is more hydrogen, and bromine will be attached to the place where there is less hydrogen. This is according to the Markovnikov's rule. So we have CH3, CH2, and then over here we already have a hydrogen, and here we have two hydrogens. So where would the new hydrogen from HBr will go and attach itself? To the terminal carbon here, and the bromine will get attached over here. So students, now the bromine is present here, and if you want to now remove this bromine through an elimination reaction and form a double bond, you can go ahead and do that. So how do you usually remove bromine through an elimination reaction? We can add alcoholic potassium hydroxide. So when you do this, a double bond will be formed. Now you might be thinking, so what is the reason for us to get the Br here and then adding KOH to get another double bond? Wouldn't it be ending up producing the same double bond here? No. In the theory parts we discussed that when you're talking about forming a double bond between two carbon atoms with the use of this type of an elimination reaction, the major product that is getting formed would be the product that has the least amount of hydrogens attached to carbons that form the carbon-carbon double bond. So if the carbon-carbon double bond gets formed here, there will be two hydrogens over here in this carbon and one hydrogen here. So altogether that will be three carbons attached to, or three hydrogens attached to the carbons that are forming double bonds. We call them olefinic hydrogens. So now if the carbon-carbon double bond is formed between the second and the third carbon, at that point, after the formation of the double bond, each carbon that is forming the double bond will only hold on to one hydrogen. So therefore, the number of hydrogens connected to carbons producing double bonds is going to be in total 2. So one less than the product that was formed here when you have a double bond here. So having lower amount of hydrogens like that is going to be producing the more stable molecule. So therefore, you will have the double bond here now, CH3, CH. There's only one hydrogen connected to each of the carbons that are producing the double bond. Right? So there are only two hydrogens here. But earlier on, when the double bond was present here, there were altogether three hydrogens. So when you are trying to carry out this alcoholic potassium hydroxide based elimination reaction, you can be sure that the major product is going to be this. So now, now in the question they say whatever the isomers that are getting formed, you can disregard them. And then at this point, you can add cold dilute alkaline potassium permanganate. So at that point, you will have a glycol formed. The double bond pi bond will break, and across the double bond you will have OH groups attached like this, forming our glycol or forming our diol. So this is how we can carry out this conversion. So you can see we have this particular initial alcohol, and in order to get to the final product that we need to obtain, as I mentioned earlier, by observing the fact that this is a diol, we could assume that the previous step we had an alkene. So you have to work towards getting a double bond between the second and the third carbon, and that is what we have done here in these couple of steps. And after getting the double bond, we can add a dilute cold alkaline potassium permanganate solution to produce the final product that we have over here. So if you want to have a look at the overall reaction, you can see the overall reaction here. Right, so that is the answer to the first question. Consider the reaction between propanone and sodium cyanide. So we have been given a reaction and we have been given the product as well. Main organic product has been given. In the statements given below, cross off the words or symbols that are not suitable. So before we move on to the question part, let's identify the mechanism or what happens in this reaction, because there are questions about whether this is an electrophilic reaction or a nucleophilic reaction. So that means they are related to the mechanism of this particular reaction. So we will see what the mechanism is. So we have CH3, C double bonded O, and again we have a CH3 here, and a cyanide group. So in the cyanide group, the negative charge is on the carbon, students, don't forget that. So over here, the carbon-oxygen double bond, due to oxygen being very electronegative, electrons will be pulled towards, the bond electrons will be pulled towards oxygen, making oxygen partially negatively charged, leaving carbon partially positively charged. Or in other words, carbon is now slightly electron deficient, or electron density around carbon is slightly decreased, which makes it susceptible to attacks from a nucleophile. So cyanide group, there's a lone pair on carbon and a negative charge on carbon as well, making cyanide group a nucleophile. So an attack will originate from the nucleophile, and this particular carbon will be attacked, and the pi bond between the carbon-oxygen double bond will break, and the electrons pertaining to that bond will be given to oxygen atom, forming CH3, CO. So there is a lone pair now. Actually, there are two other lone pairs on oxygen, but we have only represented the lone pair that oxygen gained due to the breaking of the bond, right? And then we have CH3 here. Apart from that, the cyanide group is now attached here. So there's no negative charge on carbon anymore because we used both of the electrons to form a bond between the carbon atom here. So now, students, H plus in the medium and this lone pair found on oxygen can work together to form a bond there, will form the final product that we see over here, OH here, CH3 here, and cyanide group here. So this is the basic mechanism. So what we saw here was a nucleophile. That nucleophile initiated the reaction. So this is a nucleophilic reaction. And earlier around this carbon there were only 3 groups. Now there is a new group. So a group got added to this carbon. So therefore this is the addition reaction. So this reaction is a nucleophilic addition reaction. So let's go back to the question, the first question. I have to cross off the words or the symbols that are not suitable for this sentence. So propanone undergoes, is it electrophilic or nucleophilic? Nucleophilic. So I have to keep that and remove the unnecessary or not suitable word. So propanone undergoes a nucleophilic. Is it addition or a substitution reaction? It is an addition reaction, so I can cross off substitution. So the answer is propanone undergoes a nucleophilic addition reaction. The OH group in the product is formed due to the reaction between the carbonyl group and Cl and water, or water and H+. So if you see the step before the H plus is added, so we had CH3, this was the intermediary stage. There was a lone pair on this carbon, there was a negative charge. We have CH3 here, and at this point we saw the cyanide group was already connected. So here H plus in the medium, obtained or was given the lone pair on oxygen. So the answer in this case is water and H plus. Actually, this is one single answer, water slash H plus. So we will be taking water and H plus as the answer, because sometimes we can actually indicate this H plus this way as well. In water, H plus and water can form this ion H3O plus. We can rewrite this the following way. Right, so when this particular hydrogen, due to it being partially positively charged, will receive the electron pair from oxygen, and this bond will break and will be given to oxygen atom, forming a neutral water molecule. So again, even this way of writing the this part of the mechanism is correct. So the answer is water and H plus. So the answer that is not suitable is Cl minus and water. Right, so water and H plus is basically the equivalent of us writing H plus slash water. Alright everyone, so now we have the carbonyl carbon in propanone reacts as an electrophile, nucleophile and free radical. The carbonyl carbon in propanol acts as a, now carbonyl carbon in propanol looks this way. Right, so the carbon carbon here is partially positively charged, while this oxygen is partially negatively charged. So I told you this is electron deficient. So electron deficient groups act as what? Electrophiles. The first answer. So carbon carbon acts as an electrophile, not a nucleophile or a free radical. So the answer is electrophile. I have to cross off the rest of the other options. The hybridization of carbonyl carbon of propanone is, now hybridization of carbonyl carbon of propanone. How many groups are attached to the carbon of carbon that is indicated here? The carbon carbon, there are altogether 3. So the hybridization at that point would be sp2. So for this question, the answer would be propanone is sp2. So I have to cancel off the other options. And then they ask, during the reaction, the hybridization changes to what? So when the reaction happens, the product that is formed is this CH3, OH, CH3 and CN. So here we can see this carbon has altogether, that carbon has altogether 4 groups. So this carbon now has a sp3 hybridization. It has sp3 hybridization. So the answer for the second part is sp3. So we can leave that part there. Compound X has the C8H18O6 molecular formula. X contains a hydroxy group, and when it is reacted with excess ethanoyl chloride, a product with relative molecular mass of 378 was formed. Calculate the number of hydroxyl groups found in the compound. Now students, this is a very good question. I hope you will attempt the question before I provide you the answer, right? So you can pause the video and maybe attempt this question. Now, when attempting the question, one of the things that you have to remember is we are talking about an alcohol. It could be a monohydric, dihydric, or trihydric alcohol. And when alcohols are usually reacted with carboxylic acids, and we are very clearly given, we are reacting this with ethanoyl chloride. So it's not a carboxylic acid, it's an acyl chloride, but we have mentioned that acyl chlorides are more reactive than carboxylic acid. So therefore, acyl chlorides will readily react with, or very easily react with alcohols to produce esters. So in this case, we are given the acyl chloride, ethanoyl chloride, CH3, C double bonded O, Cl. This is the acyl chloride we are given. So, and then imagine we are given an alcohol like this, ROH. So this is our compound X, let's say. This entire thing is our compound X. Now, when we don't know whether I can't say that this is the compound X because we have no idea whether the compound X has only one OH, two OH, or three OHs. We don't know. So therefore, I'll just say this is a alcohol, general formula of an alcohol, just to indicate what happens when alcohol is reacted with our ethanoyl chloride here. So if the alcohol is reacted with this ethanoyl chloride, you can see that the Cl group as well as this hydrogen from the alcohol will be removed, and we will form CH3O, and this alcohol O and R group. So this part came from the alcohol, right? Will be formed along with HCl, So when this reaction takes place, we say alcohol undergoes an acylation. So when this happens, this section, CH3CO section, is added to the alcohol, but we are replacing a hydrogen that the alcohol has. So if you take a look at what type of mass difference is happening here, we are adding this particular part, so obviously that mass will be gained while losing the mass of the hydrogen, because hydrogen goes away, right? So this entire section that is added here, is what replaces this hydrogen, right? So if you take a look at what type of mass difference happens to the alcohol while it is undergoing acylation, we can calculate the mass difference like so. So we have this section that is newly added. So what is the mass of this section? We have 2 carbons, so therefore that is 24. Each carbon has atomic mass of 12. 3 hydrogens and 1 oxygen. So this is 13 and 43. So this section with a mass of 43 is added to the alcohol. So alcohol is losing a hydrogen. So therefore, the overall mass difference is going to be 43 minus 1. Why? Because although this section has a mass of 43, there was a hydrogen here. That hydrogen is replaced by this acyl group. So therefore, the overall mass difference we can observe when one alcohol group undergoes acylation is this. So we can write when one OH group or hydroxyl group undergoes acylation with ethanoyl chloride, 42 molecular mass difference will occur. A 42 molecular mass difference will occur. So that is for one hydroxyl group. If there are two, then 42 into 2 is 84. So we know this detail now. And the question says, in the beginning, the question tells us the molecular formula of the alcohol, C8H18O6. C8H18O6. Now don't think this because there are 6 oxygens, all of them are alcohol oxygens. Don't write there are 6 oxygens, so can form 6 hydroxyl groups, so therefore this has 6 hydroxyl groups. If you write the answer like that, that will be wrong. So we can find out the molecular mass of this substance or this alcohol. So we have, or this organic compound here has this molecular formula. So the mass of it will be 8 multiplied by 12 added with 18 multiplied by 1 added with 6 multiplied by 16. Right, so 8 into 2 is 16, and then we have 96 here plus 18 here plus again we have 96. 6 into 6 is 36, 6 into 1 is 6, so you have 96 here. So when you add them all together, we can see 6 plus 8, 14 plus 6 is going to be 20. And then we have 9 plus 1, 10, 10 plus 9 is 19 plus 2 is going to be 21. So 210 is going to be the overall molecular mass of the substance. So this was the mass. So this was the mass of the compound X that contains the hydroxyl groups. So compound X that contains the hydroxyl groups had a mass of 210, molecular mass of 210. And then after it has been esterified, or after the esterification process, now this is an ester. Now the ester has a mass, according to the question, the ester has a mass of 378. It has a mass of 378. Yes. So that means after the addition of acyl chloride, which is CH3COCl, the final product had a molecular mass of 378. And we know with one hydroxyl group, 42 of a mass difference is there, but here there's a massive mass difference, not just 42. So then we have to find out how much of a mass difference has been here. So the overall mass difference is equal to 378 minus 210, which is going to be 110. 168. 168. So if one hydroxy group brings about a 42 molar mass or 42 molecular mass difference, then we can figure out how many hydroxyl groups are present here. So we can write number of hydroxyl groups is equal to the overall mass difference divided by mass difference brought by only one hydroxyl group. Only one hydroxyl group. So when you divide this, we can see this is this can be solved very easily. Actually, when you divide this, the answer would be 4. When you multiply 42 by 4, you get to 168. So the answer is 4. So that means the compound X, calculate the number of hydroxyl groups found in compound X. So we can write the compound X in total has, compound X has a total of 4 hydroxyl groups. We can write that down here. Compound X has 4 hydroxyl groups. So that is the final answer, students. So now we can move on to the next question, or B part of the same question. A, B and C are isomers. A, B and C are isomers of the amine with the same molecular formula C4H11N. So we have this molecular formula, and A, B and C are amines, and they are all isomers of one another. When these amines are reacted with sodium nitrite and HCl, alcohols D, E and F are produced. So we will write this down. So these are all amines. A, B and C. These are all amines. These are all amines, and when we react them with sodium nitrite and HCl, we produce D, E and F. D shows a fast reaction with Lucas, right? D shows a fast reaction with Lucas, or we say Lucas reagent. So it's a fast reaction. But E and F, what do they say about E and F? E and F does not show a reaction with Lucas reagent. So then we can say with Lucas there's no reaction. Right. And E and F can be oxidized to G and H in order. G and H both give precipitates with Brady's reagent. They also can reduce Fehling's reagent, identify the possible structures of G and H. So E and F produce G and H. And they can react with Brady's. So anything that answers to Brady's are what? Carbonyl compounds. So both of these, G and H, are carbonyl compounds. Right? Apart from that, they also react with Fehling's. Now, what out of the two carbonyl compounds are usually going to be answering to Fehling's reagent, or positive answers to Fehling's reagent. Now, Fehling's or Benedict's will be used to identify aldehydes from ketones. Ketones will not answer to these, but aldehydes will. So that means if G and H show reaction with Fehling's, that means these are aldehydes as well. These are aldehydes as well. So we know now G and H are aldehydes. So based on that, we can now attempt this question. So students, in the beginning of this question, they very clearly state that these are amines. But what type of amines? We have primary amines, we have secondary amines, we have tertiary amines. So primary amines are amines basically where you have only one. Primary amines look like this, right? We have only one alkyl group connected to the nitrogen hydrogen part of the molecule. So this is a primary amine. Secondary amines will have two alkyl groups. Tertiary amines will have three alkyl groups in it. So only primary amines can show this reaction. Sodium nitrite and HCl will turn primary amines into alcohols. In this case, we have ROH. The amine group will be turned into an OH group, right? So a primary amine can be turned into an alcohol. So over here, all of these are amines. We can be now more specific. They are primary amines. They are not secondary or tertiary amines. If that is the case, they will not show a reaction with sodium nitrite and HCl. And DEF are alcohols. Alcohols. And even there, we can actually now see that we are using Lucas reagent, zinc chloride and concentrated hydrochloric acid. So when it comes to Lucas reagent, we know tertiary alcohols will quickly react with Lucas reagent to produce chloroalkanes. So actually with Lucas reagent, tertiary alcohols will produce a turbidity immediately. However, secondary alcohols will take about 10 minutes to show a turbidity, whereas primary alcohols will not show a reaction in a reasonable amount of time. So that means, students, here D has shown a very fast, immediate reaction with Lucas. That means D is a tertiary alcohol. D is a tertiary alcohol. So this will indicate that the D is a tertiary alcohol. You can write it with words, tertiary alcohol. And since E and F do not show a reaction with Lucas, we can say they are primary alcohols. So now we have identified that D is a tertiary alcohol and E and F are primary alcohols. So now, students, we have a clearer picture of what is happening here. We know now the D produced is a tertiary alcohol and E and F are primary alcohols. And of course, D cannot be oxidized with oxidizing agents like acidified potassium permanganate or acidified potassium dichromate. However, we can oxidize E and F. Primary alcohols can be oxidized. You can oxidize primary alcohols all the way up to carboxylic acid, but if you use PCC, you can oxidize it up to aldehyde or a ketone based on the alcohol type, right? So in this case, if you use PCC, primary alcohols can be oxidized up to aldehydes. Primary alcohols can be oxidized up to aldehydes. So what we have done here is that if you had used a strong oxidizing agent like acidified potassium permanganate or acidified potassium dichromate, these primary alcohols will go all the way up to carboxylic acids. However, primary alcohols can be converted to aldehydes if you use a reagent like PCC. So now G and H are aldehydes, we know that, and aldehydes will answer to Brady's reagent. Brady's reagent is 2,4-dinitrophenylhydrazine, 2,4-dinitrophenylhydrazine. Any aldehyde, any ketone will produce orange or yellowish precipitate in the presence of 2,4-DNP. Apart from that, aldehydes can react with Fehling's reagent and Bendix's reagent, Tollens reagent. So these are tests that can be done to identify aldehydes. But ketones will not answer to these tests. So G and H answer to these tests, indicating G and H are definitely aldehydes. So now let's identify each of these compounds, right? So if D is the key to identifying all of these, because we can see D is a tertiary alcohol, and we have been given the molecular formula of the alcohols that are getting produced. DEF molecular formula is given. C4H10O, C4H10O. So let's identify what D would be. D has to be a tertiary alcohol. That means to the carbon bearing the OH group, there should be 3 alkyl groups. So we are only given 4 carbon atoms. So we can add 1 CH3 group each to each side to form this particular tertiary alcohol. Right now, we have utilized all of the carbon atoms that are available in the molecular formula C4H10O. So let's see whether there are 10H and 1O. So 1O is okay, and we can see there are 9 hydrogens here plus 1, 10. So this particular D structure is agreeing with the molecular formula that is given here, C4H10O. Then A and B, or actually D was produced by A. So we can see A is going to be, if this was D, A should be something like this, CH3, C, NH2, CH3, CH3. You have to remember, when A underwent a reaction with sodium nitrate or nitrite with HCl, sodium nitrite and HCl, sodium nitrite and HCl, you formed that product. So A is this. Now it is time for us to identify B and C and E and F. So we'll work with E and F first, because we know E and F are both primary alcohols. That means to the carbon bearing the OH group, there can only be one other alkyl group attached. The other 2 bonds must be hydrogens. So the formula is C4H10O. So we have already utilized 1 carbon here. We can connect the rest of the carbons like so. So then at that point, CH2, CH2, CH3. So we have 7 carbons here, 8, 9 and 10. We have 7 hydrogens, 8, 9 and 10 hydrogens, only 4 carbons and 1 oxygen. So this adheres to the molecular formula. So this could be our E OF. Actually, EOF is interchangeable. There is no a specific method that is given here to identify B and C both are primary alcohols. So those two can be interchanged. E and F and B and C can be interchanged when you are providing answers. So if you call this E, at that point F would be this. Don't forget, even in F, it has to be a primary alcohol, so there should be two hydrogens connected to the carbon bearing the OH. And we can attach a CH3 group here. This is still a primary alcohol. This is still a primary alcohol because all these this CH3 branch is not directly attached to the carbon bearing the OH. If it was attached to the carbon bearing the OH, it will be a secondary alcohol. All right. So now in this case, this can be named F. If this is F, then we can write the structures for B and C as well. So at that point, in place of OH, we can add NH2, right? So CH3, CH2, 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 NH2. This is the structure of B, because B produces E. If that structure is E, then this has to be the structure of B. And then structure of C would be this. So you can see now, if that is a structure, of F, this has to be the structure of C. This has to be the structure of C. So now, students, we have identified the main structures for A, B, and C, and D, E, and F. D, E, and F are also identified. All right. So now, since we know the structures, we can move on to the next part. So the next part, we are going to be asked to draw G and H, right? G and H. So G and H can be formed from E and F. So E was this CH3, CH2, CH2, CH2OH. There are 4 carbons here, 1, 2, 3, 4. And when this undergoes oxidation in the presence of PCC, you will be producing this aldehyde. It's a controlled oxidation. You'll be producing this aldehyde. This aldehyde will answer to Brady's as well as Fehling's. So this is our G. This is our G. Since this was E. Then if you are moving on to F, F would be CH3, CH3, CH2, OH. Again, this is also a primary alcohol. So when primary alcohol is reacted with PCC, you form CH3, CH3, C double bond O and H. So this is another aldehyde. that we form over here, even that aldehyde will answer to Brady's reagent, forming an orange color precipitate. So what we have over here is H. What we have over here is H. So these are the main reactants and the products that we observe in this particular question. So the question is to identify the possible structures for A, B, C, D, and A, B, C to all the way to H. They are only asking for A, B, C, G, and H. But in order to get to the answers, we'll have to write and have an understanding about the structures of the structures of all of the compounds, right? Or the question asks about A, B, C, and G, and H. We have written here all of the structures for your knowledge. So now we can move on to the next question. So let's take a look at the third question. Observe the stepwise synthesis given below and identify the structures of the compounds E, F, and G and reagents S, T, U, and V. So we have compounds formed here and then some reagents we need to add to make these conversions. So when you take a look at this, one thing that you can identify is we are starting with a benzene ring, right? And we are adding AlCl3. So this could be a Fiedel-Crafts alkylation reaction or an acylation reaction. That means we might be adding a alkyl group to benzene or an acyl group to benzene. And there's a reaction here that requires two steps. So could be a two-step reaction. So you can observe that. And then PBr3 is added. So that means if you're adding PBr3, we might be converting a OH group into a Br group. OH group into a Br group. So that means there might be a Br group here. So if that is the case, when you use a Br group and do something and come here, what can you do with the Br group? You don't see the Br group here. PBr3 is used to add Br group. We don't see the Br group here. Why? Because we have done an elimination reaction, right? We have done an elimination reaction. So that means this could be alcoholic KOH. This could be alcoholic KOH. And there can be a Br group here. Or there can be, yes, in this case a Br group. Over here, there can be an OH group. So we do have a little bit of an understanding about what is going on here. So with the information that is given here. So let's say that we have the double bond formed here, and we currently are under the impression due to the addition of PBr3, there would have been a bromine connected to a carbon here. That means there was a OH group that was converted into a Br group. And now in this particular product, the Br group is no longer going to be seen. So that means we have added alcoholic KOH. So V is KOH, not just any KOH. We don't have enough space to write the answer here, so I'll write it here. Alcoholic KOH, right? So the answer over here is alcoholic KOH. And at that point, students, you have to understand if the Br was here, then if you are reversing it, you can add hydrogen to the position where there is more hydrogen here and Br to the position where there is less hydrogen. So G would be, since there's not enough space to write the answer inside this box, I will write it outside. So G would be this. I will connect the bromine here and hydrogen to the place where there is more hydrogen. So CH2, CH3. Right, so this is G. This over here, what you have drawn is G. So we got a bromine here by the addition of PBr3. So that means F over here would have had a OH group here instead of a Br group. All right. So now, students, we can see, if you want to get to that point, now we know we are using anhydrous AlCl3. We can't get to that point just by adding an alkyl group here. Alkyl group is not going to be very reactive in order to produce that thing over here in the F position or F product. Now imagine if you add an alkyl group over here with the use of anhydrous AlCl3 to benzene, an alkyl group is not easily converted into this, right? Alkyl group is not easily converted into this. Alkyl groups are not very reactive. So then what is the only option we have? We can attach a acyl group, right, through Fiedel-Crafts acylation. So since we need to have this CH2CH3 group, so students, we can see that there is this section CH2CH3 and CH2CH3 over here as well, but they are connected to this carbon. So if you get an acyl chloride that has 3 carbons in it, it will be easier for us to move forward. So we are going to attach a acyl chlorides with 3 carbons in it. So S over here is going to be propanoyl chloride. CH3, S is going to be CH3, CH2, C double bond O, Cl. So through this propanoyl chloride and anhydrous aluminium chloride, we can carry out a Fiedel-Crafts acylation reaction. So we can add this entire section into the benzene ring. So the product that is formed here, the E product that is formed here is going to be this. I will have to draw it a little further down, otherwise you will not be able to clearly observe the E product. So I will draw it here. So we are almost there now. So this is product E. So product E can easily be turned into F by doing what, students? We can add Grignard's reagent and then water. So addition of Grignard's reagent is going to be how we produce the final answer, right? So we have T. As T, we can write CH3, CH2, MgBr. You can take MgCl as well if you want. And as a second step, this has to be in dry ether, right? In dry ether. And then in the second step, we can add H plus H2O. You can write an acid as well. So at that point, you will form the F product. So students, from there onwards, the rest of the mechanism is already completed. So since it is somewhat not clear when it is written over here, we can actually rewrite it. We are starting with benzene. And then we are adding this propanoyl chloride with AlCl3 and anhydrous AlCl3. You will be producing this product. So this was E. That was E. Then we can react E with one CH3 CH2 MgBr and second step would be to react it with an acid H plus H2O. So when you do that, you will form this product and then when we carry out a further reaction, actually when we add PBr3, OH will be replaced by Br, and then finally we can carry out an elimination reaction by the addition of alcoholic KOH. So this will produce the final product that is given to us, which is this. So students, now I hope you have a clearer picture, as the diagram over there was not that clear. So now we can have a clearer understanding of what is going on in this conversion. Alright, so with that we can move on to the next question. So now we have come to the B part of this question. How could you carry out the conversion shown below? We have C6H5 COOH. So we have benzoic acid turning into the product that is given over here. And one important observation is that there's going to be a carbon and nitrogen double bond. A carbon and nitrogen double bond is produced. And we usually observe this type of carbon-nitrogen double bond when we deal with Brady's reagent also. Can you remember? When an aldehyde or a ketone reacts with Brady's reagent, I will draw the aldehyde like this. It will be easier that way, right? If you have an aldehyde or a ketone reacting with Brady's reagent, so Brady's reagent is 2,4-dinitrophenylhydrazine. So it has the following structure. So the second position as well as the fourth position, we have nitro groups. So 2,4-dinitrophenylhydrazine. If you want, you can write the nitro group this way. And here we have two hydrogens connected to the nitrogen. So NH, there are two NH bonds. So when 2,4-DNP reacts with an aldehyde, this hydrogen and this oxygen will go off as water, and then this carbon will form a bond with nitrogen, and that's going to be a double bond. So the final structure is going to look like this. R C H N H and then the benzene ring with the nitro groups. Alright, so this is a product that is going to be a precipitate, which is going to be orange in color. So you can see a carbon-nitrogen double bond was formed here. A carbon-nitrogen double bond was formed here, and a similar double bond is present here. So that means this section would have been something like this. We can identify that section first, right? This section would have been something like this. NH2. So I'm now displaying the hydrogen bonds. Earlier, when I drew earlier, I just wrote NH2 here. Now I'm displaying the hydrogens. NH2, and then we have CH2. We know C6H5 means we are dealing with a benzene ring. So I will write it as a benzene ring. So this is one reactant we would need to produce this particular product. So that means one of the compounds that goes into the formation of this final product that we have over here. And then this section should be an aldehyde section because we have a carbon here with a hydrogen. So this section could be something like this. An aldehyde section. So that means these hydrogens, as I mentioned earlier, these hydrogens, each of these hydrogens along with this oxygen can go off, connecting the carbon and nitrogen through a double bond. Right, students? So we are now done with identifying the main two compounds that should be there in the final step when producing this product. So now we need to get to these different compounds. But I think we don't need to get to this particular compound. They have already given that to us. The only organic reagent that can be used is C6H5CHO. C6H5CHO is this, right? C6H5CHO is this. So this indicates a benzene ring. Yes, we have that. And then CHO. Yes, CHO is one carbon, one oxygen, one hydrogen. So we have been already given that benzaldehyde. Right, so now we need to somehow produce this starting from the carboxylic acid here. So students, we can do that. We can do that by taking CH. We can do that by taking acid here, benzoic acid. And we can reduce the benzoic acid to form with the use of lithium aluminium hydride, dry ether. And water. You will produce this. Now, we are still not where we want to be. We need to have a NH2 group here. So we can add bromine here, and then bromine can be turned into an NH2. So we can now add PBr3 So then at that point we have CH2Br produced. So that then can be converted to an NH2 group by adding ammonia and heating. We can get to our desired amine. So this is an amine. So this amine can now we have used 3 steps to get to that point: 1, 2, and 3. So the final step would be this amine can be reacted with, we can react it with benzoic or benzaldehyde. Benzaldehyde is given to us. We don't have to form it. It is given to us in the question. The only organic reagent we can use is this. So when you react these two together, the product that is formed is this. The hydrogens from this nitrogen will go off, and then the rest of the molecule will be present connected to the nitrogen, CH2, and then the benzene ring. So this was the desired product, and we got to that point with the use of 4 steps. So this is the answer to this question, students. Now you may use different methods, but if the method is longer than 4 or 6 steps, then you will not gain marks for that. However, if it is smaller number of methods than 6 steps, then if it is a method that has small number of steps than 6 steps, then at that point you would gain marks for that. You can also, now the main part over here is producing this amine, right? So you can produce that amine another way as well. You can react this with ammonia, so you will have the ammonia salt, and then you can heat it, right? So it will turn into an amide, and then if you take that amide and reduce the amide, you will obtain a amine, right? So that is also another path, right? You have the carboxylic acid reacted with ammonia, and the product that you receive is an ammonium salt. So you can heat it, and then you will turn it into an amide. The amide can then be turned into this amine with the use of lithium aluminum hydride. You can reduce the amide to produce this. So again, students, there are other ways of getting to the same product, but when you are carrying out these type of reactions, you have to be mindful, and you have to keep an eye on whether it agrees with the question that is asked of you. All right, so now we can move on to the next question. So students, let's move on to this part of the question. Write the main organic product of each of the reactions. So we have an oxidation happening here in the first step. Now keep in mind, you can see this is not a benzene ring that you see here. This is not a benzene ring. So therefore, this is just a cyclic hydrocarbon. And you have an OH group there. So that would mean, students, you have this type of molecule here, OH, a hydrogen, and each of these places have 2 hydrogens, CH2, CH2, not a benzene. This is not a benzene. And finally this, right? So here the OH that is connected to carbon, this carbon that has a OH in it, has 2 other carbons connected to it. So this appears to be a secondary alcohol. Why? The carbon that is bearing the OH has 2 other carbon groups connected to it, and there's only 1 hydrogen connected to the carbon bearing the OH group. So this acts as a secondary alcohol. So when secondary alcohols are oxidized, you can form a ketone. or the product that is formed here can be written this way. Right? So there is not a benzene, students. And then again, we have another similar situation going on here. We have an OH group connected to this position. So therefore, there are two alkyl groups here. Again, this is not a benzene. And when you oxidize that, you will also again produce a ketone. So I will write the answer this way. This is going to be the ketone group here, and then the product is this. And finally, when you have HCl, if it is conc HCl, only this reaction will be possible. So conc HCl and zinc chloride. So this is Lucas reagent. This is Lucas reagent. So when it comes to this reaction, what you have here is a formation of a chloroalkane. Chloroalkane will be formed. Here a Cl will be present now, and then we have CH3 here. Right, so this is the product that will be formed. This is the product that will be formed. Now, if you are using only the skeletal structures, there won't be a necessity to indicate a CH3 here. When you draw it like this, it should be clear to you. So keep in mind, when you're using only skeletal structures, be very careful when you are dealing with cyclic compounds like this. If there is no circle inside this, that means it is not a benzene, right? This is a 6-membered carbon ring without a delocalized electron cloud, so this is not a benzene. Now let's move on to the next part. Write a simple reaction that can be used to identify alcohols and alkenes separately. Alcohols and alkenes separately. So if you take alcohols, we'll represent alcohols this way, ROH, and alkenes are this way, right? So this is an alkene, CH2. So therefore, you'll have to include 2 hydrogens, like so, right? So now, we know alcohols are different to alkenes. Their properties are different. The types of reactions that they show are different. So we can write a few different reactions that we can actually use to identify alcohols from alkenes. First, we'll use a very obvious test that can be done, that is bromine water. So if you had Br2H2O or bromine water, then what happens? It'll be decolorized, right? Bromine water, yellow, brown color will be decolorized. However, what about the alcohol? Alcohol, bromine water, will there be a reaction? Bromine water, there is no reaction. No reaction. Nothing will happen. Right, we can use bromine CCl4 as well for each of these, but there will be no reaction with alcohol. Apart from that, we do know, now this is one set of tests we can do. Apart from that, we do know alcohols show a little bit of acidity. So alcohols can be reacted with sodium, right? It can be reacted with sodium, and you know sodium alkoxide will be formed. Now this is not an observation we can see, sodium alkoxide formation. You can't see that as an observation, but hydrogen gas will be formed. So this is an observation, and plus when sodium reacts with this, it is a visible observation. But just by looking at the product here, sodium alkoxide, you can't say sodium alkoxide is getting produced by looking at it, right? So observation would be the formation of a gas. But will sodium react with an alkene? Will sodium react with an alkene? No. Sodium and alkenes, there will be no reaction. There will be no reaction. So these are tests that can be done. Another one I think is a very important one is, we know alcohols can react with carboxylic acids, right, in the presence of concentrated sulfuric acid to form esters. So how do you know an ester is formed? They will have a characteristic smell. They will have a characteristic smell. They will have a characteristic smell that can be observed. So this also can be used to identify alcohols. Esters are formed, has a characteristic smell. Will anything happen when we react an alkene? Will anything happen when we react an alkene with a carboxylic acid? The same conditions. There will be no observation or no reaction. So there's going to be no observation or no reaction. So that is something you have to keep in mind. So these are some tests that can be done to separately identify alkenes and alcohols, right? These are some tests that can be done to separately identify alkenes and alcohols. So let's take a look at this question. What is the main purpose of adding concentrated sulfuric acid into the esterification process? Now, since we know we use concentrated sulfuric acid in the esterification process, but why do we do that? So in water, we can say sulfuric acid releases H+. Usually sulfuric acid, the H+ release happens in 2 steps, but for the simplification purpose, we will write that there will be 2 H+ coming into the medium like so, along with the sulfate ion. So we know that there are H+ coming into the medium due to the presence of sulfuric acid, or actually a concentrated sulfuric acid medium is going to have a very low pH, indicating a really high H+ ion concentration. So at that point, if you take an ester, let's say, or if you take a carboxylic acid, carboxylic acid will react with an alcohol, and we know the alcohol has an oxygen that can donate a proton to this carbon, which is going to be partially positively charged due to the polarization of the carbon-oxygen bonds. However, when a lot of H+ are present, this oxygen over here, or this carboxylic acid, can be protonated, and one lone pair on oxygen can be donated to form a bond between oxygen and hydrogen. At that point, oxygen will be positive. So since that is not going to be very stable, the pi bond between oxygen and carbon here is going to be broken, and the electrons of that bond will be given to oxygen. So at that point, you will have this formed, RCOH, along with OH here. So now you can see, earlier on here, carbon was partially positive and oxygen was partially negative. Here still oxygen is partially negative, but carbon is a full positive charge now. So at that point, students, carbon is very susceptible to an attack from an alcohol. Let's take a simple alcohol like methanol for this example, right? So it is quite susceptible to an attack from electron-rich species like this O in the alcohol. So there will be an attack happening, and as you know, the rest of the mechanism would take place from there onwards. So this is the reason. Making the attack of a nucleophile on that particular carbon much more easier is the reason why we add sulfuric acid to the medium. Otherwise, the normal nucleophilic addition will happen like this. And this is going to be a very slow reaction. There's going to be delta positive here, there's going to be delta negative here, and the alcohol will be present like this. And at this point, this is a partial positive charge. So this nucleophilic attack is not going to be easily done like over here. The carbon over here is a full positive charge. So the reaction is going to be catalyzed or made faster with the use of sulfuric acid. And towards the end of the reaction, H plus will again be released, which makes sulfuric acid acting as a catalyst. If it is getting used up, it will not be acting as a catalyst, but here H plus will be released. So students, that is why we consider this to be a catalyst for the reaction that is taking place when esterifications are carried out. So we have written only a section of the mechanism. The rest of the mechanism was discussed in the theory parts. So the most important part over here, the explanation over here as to why sulfuric acid is used as a catalyst is the production of this carbocation with a positive charge on the carbon, where we need to attach the OR group, or the alcohol OR group. So the nucleophilic attack on that carbon is going to be made easy due to the presence of a full positive charge. Right, students, so with that we can conclude today's question discussion. So initially we discussed the theory parts revolving around alcohols, and then we went on to the lab and conducted the experiment and actually observed all of the different types of reactions we can do with alcohols and their observations. And here in the third part, we actually discussed some questions, and we developed a good enough understanding about how to answer questions that revolve around experiment number 25 or that revolve around alcohols. So students, I hope by now you have a good understanding of the theory parts of alcohol and the type of questions that you may have to face during the exam. So students, with that, we can conclude today's experiment. I will see you again in the next experiment.